Good morning. I'm Jesse Spencer-Smith. I'm Chief Data Scientist and Director of the Data Science Institute here at Vanderbilt University, and I'd like to welcome you to our AI Training Day. Thank you for being here with us today. We're going to have two main sessions today. In the morning, we're going to be talking about transformer models. We're going to be talking about generative AI at a high level. But it turns out that understanding how these models work, how you train them, and how you interact with them is core to making good decisions about using AI. In the afternoon, we're going to be talking about how you actually train these models. What are the steps that you take to train the models, and what infrastructure is available for you to be able to do this? So it's the more technical session. But I encourage you, even if you're not a technical person, to stick around for the afternoon if you're so moved, because I think you're going to be surprised at just how straightforward it is, actually, to prepare and to train these models. So I'd like to start out by asking the different members of our staff to stand up and to wave. So Miranda Shirk, data scientist on our team, also a graduate of our master's program, Umang Chowdhury. Also, data scientists on our team. These folks are going to be teaching in the afternoon. Sharo Bell Professor Bell is going to be here this afternoon as well. In addition to being a senior data scientist at the Data Science Institute, she's also professor in computer science, professor of the practice, and also director of our data science minor. So if you're a student here and are not yet a data science minor, you'll want to talk to her. And then we have other staff members as well. So we have Damani Smith, who's going to be helping with microphones. And we also have our assistant director, Amber Miller. And then we also have Miguel. So Miguel Nunez, I'd like to give a round of applause for Miguel because he organized all of this. So, a few additional housekeeping items. We are recording this session. It's going to be available later, so if you have friends or colleagues that were not able to be here, we'll have the recording available on our Data Science Institute YouTube channel. But this does put a few restrictions on us. So we're going to want to be using the mic. So if you have a question, I'm going to ask you to raise your hand and to be patient for just a moment while we get the mic to you. So just be sure to raise your hand if you would, if you have a question. We'll get the mic over. Oh, yes.
Just like this.
Just like that. Yes, exactly. So it'll take a moment for us to get the mic over to you. If you would like to exert some agency in this, then you can also go up to the mic and ask a question there, whichever you would like to be able to do. At lunchtime and also in the afternoon, we'll also have TAs here as well. There can be 4 members of the Data Science Institute Master's Program. I think 3 second-year students and 1 first-year student. But they're going to be here to answer questions, also to help you get set up if you weren't able to complete setups this morning for this afternoon session. But also I've been having conversations with a number of you already, and you're starting to get ideas about how you might use generative AI. And conversations with both our staff folks and also with our TAs is going to be a great way for you to actually explore further about how you might be using this technology. So let's go ahead and get started. And I'm going to start actually by asking you some questions. So those of you who've used generative AI, and that means ChatGPT or Claude or any of the other models, what have you used it for? First of all, hands up, who's used generative AI here? All right, so a lot of folks, not everybody, but that's fine. Okay. Hands up if you're willing to share what you've done with it. It can be anything. Who would be willing to share? Okay, great. So, Damani, we have a volunteer right back there.
Hello everyone, I'm Davey. For my law class, after reading whatever Supreme Court case, I asked ChatGPT to give me a background and analysis of the case so I can go back and kind of check if my understanding was correct.
So you use it to get background analysis of the case. Do you upload the entire case to it and have it?
Because they're like older Supreme Court cases, it already exists within its knowledge base.
Interesting. So you are counting on the model sort of having already learned about the case. How well does it do? Does it make mistakes?
Not for the older Supreme Court cases.
Okay. We're going to return to this. So when the model has been well trained on something, it doesn't make mistakes. Okay, good to know. But flip side that is, if it's a newer case, it may not know it as well. Great. Other use cases. We'll do here and then we'll do here. Great.
I created a specialized GPT, as GPT 4.0 allows you to do, called it Patent Attorney GPT, so that I can use it to create homework for a new class, IP for engineers and scientists. And I also used it to, I tried it for grading and feedback to the students, but I didn't really use that. It was way too strict. So, but for my class, I used it to create homework in a jiffy. It was really fast. Mini cases on IP and the answers to them as well, but I went through them to make sure they were all okay. I'm not sure about the Patent Attorney GPT. I haven't tested it really hard to see what sort of stuff it will give me, but it has some suggestions at the bottom, the right claims for an invention and whatnot. I haven't gone down that road yet.
Fantastic. So you've really jumped in. So here, you actually using GPT-4, one of the, up until yesterday, probably the strongest preeminent model until Claude 3 was released yesterday morning. And you also jumped in and you created what's been called a GPT. OpenAI calls this a GPT, which allows you to upload some documents and then do some work with those documents. Okay, so we're going to be talking about that, exactly how that works and what are the good uses for that and what are some alternatives to that as well. So wonderful. And then the last problem that you had was that when you had to provide feedback or grade the students, it was too strict, which is interesting. So we're going to talk about how you shape the behavior of the generative AI. All right. Oh, either it's too strict or you're too lenient. One or the other. Got it. Yes, so and right up here, Damani. Thank you.
Thanks. Well, I've used it for a lot of different things, ChatGPT that is. One of the first things I did was ask it this: in the style of Chaucer, please explain how to replace the carburetor on a 1969 Camaro. And what it came back with was hilarious and delightful. So you can actually amuse yourself with it. But more seriously, I have used it for very pressing code issues. If I'm trying to write code for one of my classes and I can't quite figure out how to do something, if I explain very carefully what it is I'm trying to do, it comes back pretty much with the right answer.
So a key thing here, so in addition to having fun and seeing if you can replace the carburetor, is that what it was? But you also asked it to write code for you, but you said something really important there. If you describe exactly what you want to do, then it will do a good job. All right. So these are good use cases, and some of us have not used ChatGPT at all yet, and that's okay. Let's talk about the flip side. When have things gone wrong? Who here has asked a question or gotten misinformation from a generative AI model? Let's go back here. Let's see. Oh, well, actually, hands up again. Just go ahead. Yes.
Oh, I guess this is both when it goes really well and really bad. I would describe random items in my fridge and in my pantry. And it would come up with fantastic recipes, very detailed ones. And I, of course, have to act as a chef consultant and tell me blah, 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 exactly what to do. But yeah, it's fantastic recipes and some really weird ones. So it's both very good and very interestingly bad. But yeah.
So some other things that have gone wrong. So who else? Okay, let's go back here. When things go wrong. Oh, and wait for the microphone. It's coming.
I used it for a class. I wanted a definition. I wanted the definition of a positive semi-definite matrix, and it gave me a right definition, but that wasn't the one that was like taught in the class. So it's like it was based on some finding out the value of some eigenvalue or something, but we weren't taught that, so it was kind of useless. Yeah.
So you asked a question, and it gave an answer, but it was actually not the one that was in the correct context. So it wasn't the right answer. Let's get one more a problem that people have had with a ChatGPT.
Thank you. I asked the ChatGPT to write a book report on a book. It made up a small detail, completely fake. It's not in the book.
Fantastic. All right. So now you've had examples, really powerful examples of generative AI, ChatGPT, doing useful things. And you also have had examples of generative AI making mistakes, making up things. And sometimes people call this, how many people have heard the term hallucinations? Okay, so you've heard the term hallucinations. So what we're going to be talking about today is actually how these models work. How do they even do this? Because 16 months ago, there was nothing that the general population was aware of that could even do these kinds of things. And when the model does something that we're not expecting, is the model doing something that is fundamentally wrong? Is it broken? Because that's often what we think when we talk about hallucinations. Something's broken, therefore it needs to be fixed. Well, it turns out that it's a much more complex issue than that. And that's what we're going to be talking about today in this morning session. One or two more quick questions. Where do you suppose all these capabilities come from? How does the model know how to do these different things? The same model which writes computer code can come up with recipes and come up with a book report which is generally correct but makes up some issues, makes up some items. Anybody have some ideas about where this comes from? Where does all this knowledge come from?
Also, Jesse, make sure if they have a question, they can stand up to make it noticeable for the camera.
Okay, great. Great. Stand up would be terrific. Thank you.
So it is a statistical model trained on the probability that the next word follows all the previous words. Makes it seem like it knows things.
Now, this is fantastic. Okay, great. Wonderful. I'm going to ask you about this again in just a little bit. So that is absolutely correct. And yet, it's not quite an answer, though, is it? So it's predicting the next word. We're going to be talking about exactly what that means. But where did it learn these relationships? Anybody have an idea? Okay, then look around. Look around at all the people who are around you. And then sort of look around at the people in the town and the world. It comes from us. The models are trained on our writing. The model is trained on our interactions. So that's where the knowledge comes from. We are generating the knowledge which the models learn. So what's special about the models? They're general purpose learners. That's the essence of everything with generative AI. We have now general purpose learners. So let's talk about, in general, how these general purpose learners learn and then what that means about their proper use and how we can use them better to solve the problems that we have. All right, I'm going to start with just a simple visualization here of a model. So if we could go and switch to my screen. So in a moment, you're going to see up here a simple graphic of a model, and we're going to talk about the elements of this and how these all fit together. So this is from a book, Natural Language Processing, way back in 2022. But this is generally what's happening with the models. So we put something in. This is the context, and this can be the chat that you start. And then there's a token encoding. Then you get this thing called embeddings, and then you have this decoder stack and hidden states, and the next word prediction. So we're not wrong, right? This is next word prediction. But let's dive into more about what's actually happening here. First of all, this is a transformer model. Generative AI rests on the use of decoder transformer models. All that means is it's a particular model architecture which is, as we just said, a powerful general purpose learner, and it does just one thing, one small thing. This is all that it does. Given context, predict the next word. A little bit of an oversimplification. We're actually predicting the next token. We'll talk about that in just one moment. But that's really all that it's doing. But when you all use ChatGPT, it doesn't just return a word, right? It returns sentences, conversations. So how do you suppose that it does that? How about this? You take the word that it produces, put it back into the context, and then run it again. So as it produces the next word, you put that back into the context, run the entire thing again, and it produces the following word. And you loop around and you continue doing this. How many of you have used GPT-4 and you've watched it as it's generating the text and it pauses for a moment and then it continues on? It's doing that because it's actually actively predicting the next word. You're watching it figure this out in real time. So this is what's called an autoregressive model, meaning that once it produces this next word token, all the rest of the tokens that come after that are going to be guided by what this word was. Why? Because it goes back into the context. So think of a loop here. Produces the next word, loops around. So one visualization that I want to start you having in your head is that the model is autoregressively figuring out and then going in a particular location. Where does it go? It's driven by two things. One, what it's been trained on. But it's also guided by what's in the context. So if you have a very short context, quite literally, it's not too sure where to go. If you have a long context and more description, so for example, when you were trying to write code, you had to explain exactly what you wanted. Why? Because with a long context, now it's much more likely, the probabilities of where it needs to go are much clearer. The path is clear because the context was better. So let's talk a little bit more in detail about this. Know that we're going to go through this. So up until break, we're going to be going through. We're going to have a break around 10:30, I think it is, to have some coffee. But up until then, we're going to be going through this. We're going to be talking about what generative AI does, and we're going to be talking about how you go from simple prediction of the next word all the way to the chatbots that we see and that we work with every day. So what you're looking at here is a deep learning model. So it's a particular type of architecture, and what's hidden here, what you don't quite see, is that there are massive numbers of connections, especially here in the decoder stack. So imagine an artificial neural network where you have nodes that are connected, and just know that what you have here is a setup that you can train through something called backpropagation, and we'll be talking about that a little bit more in depth. But in essence, it is a straightforward deep learning network. There's nothing all that special about it, actually, but there are a couple of things you have to keep in mind. One, this first step, token encoding. Deep learning networks can't deal with words. You can't put a word directly in there. Now, counterintuitive, right? Because we use it to generate words all the time. The trick is we have to turn those words into numbers. That's the very first step. So token encoding means that you take your words and you turn them into numbers, integers. So 42 might be cat. 49 might be dog. So every word needs to be turned into a number. And it turns out that's actually not a good idea to take every word and to turn it into a number, because then dogs would have a totally different number than dog. That's not a good idea. You want to have some commonality there. So it turns out that the sensible thing to do, a good approach that works, is that you break the words down into bite-sized pieces called tokens. So these are subwords, and so dog is very common, so it probably has its own number. Other words that are less common, like lectern, probably might be broken down into two different tokens, lect and turn. Turns out there are lots of different ways to do this, but you can make good decisions or bad decisions. How many people have tried to use ChatGPT in another language? Okay. How many people found it did not work too well in their language? Okay, great. What language did not work well in? In Spanish? Okay, didn't work too well in Spanish. What are some other languages? Anybody try? Okay, what language did you try? Medieval French did not work with medieval French. Okay, good. What other languages did not work well? You have another one, actually. What? Hindi. So it turns out when you take this first step of the token encoding, if you don't account for multiple languages beforehand, it might be terrible in some languages. Why? Because the choice that you make for the words and subwords may not work for all languages. This is why ChatGPT, and even GPT-4, isn't all that great in Arabic, for example. Why? Because when the initial decisions were made around token encoding, they didn't think as much about other languages. Yes, the model could learn them, but if you have a word in Hindi, for example, in English, that same word may be one token, but in Hindi, it might be 8. And it turns out that once you decide how you're going to be doing your token encoding, you are stuck with it. Because the model does not know about cat. The model knows about 42. And if you try to rearrange things later, you can't. The mapping is done. So, token encoding. So have you ever heard about how much it costs to run models in terms of numbers of tokens? A few folks. Okay, how about token length? A few other folks. And when you read the more detailed reports, it'll talk about, it'll use the word tokens. This is exactly what it's talking about. Why would you talk about being charged by how many tokens is in the context and how many tokens it uses? Think about what we just said. You put some context in there, some words. Let's say that it's 30 tokens. Those 30 tokens need to be run through. That's compute. So you charge based on the number of tokens. And let's say that it then produces some text afterwards. It produces a token. It might be a word or might be the beginning of a word, and then you have to rerun. So when you start hearing about generative AI and tokens, now you know what it means. Tokens are the numbers that have been assigned to words or to subwords. And that is the coin of the realm. That is how the model actually works with and learns the text that you put in. Okay, now it starts to get a little bit strange. Token embeddings. So here's the trick for token embeddings. Does anybody remember whether 42 was cat or 49 was dogs? Was it? And yeah, 42 is the answer to life, the universe, and everything. But was it cat or was it dogs? Is there anything inherently cat-like about 42 or dog-like about 49? We just chose that. Embeddings is the very first step that you take to identify a word with something that's meaningful. And in this case, it's by creating a semantic space. So what this means is that instead of having a number, here's cat. And now cat is actually a vector. It's a series of numbers. It's a location in a high-dimensional space. Here, I could give you the coordinates in this room, assuming these are axes along these walls here. And I could say, oh, this point right here, cat, is at 632 by 562 by 1,000. So I could give you the 3D coordinates of this. And the idea here is that like words, like concepts are closer together. So cat might be kind of close to lion, might be close to tabby, furry might be a little bit further over here. So the space actually has meaning. And so now when I give the coordinate of cat, I identify 42 with this vector. Now it has some meaning. And it turns out that it's extremely useful, and it turns out this is key to understanding what these models are doing. So let me take a famous archetypal example that's used quite a bit. Let's say that here we have king. So here's the coordinate of king. And what are some concepts that will be close to king? And these you can just shout out, and then I'll repeat it. What concepts or words might be close to king? What's that? Crown, tyranny, crown. Oh, I think crown's about right here. Tyranny is probably right here. Fantastic. Okay, very good. Oh, over here is the concept for man. I'm going to do some math. These are two vectors. And if you're unsure what vectors, that's fine. Think of them as just coordinates in space. But if I were to subtract one from the other, I would end up probably about here. What word is close to this? So it might be president. So king minus man could be president. What are some other words that are close by, maybe? What's that? Queen? Oh, could be. Let's do some more math in a moment to see if we can get to queen. But before we get there, if it's king minus man, what else could it be? Prince could be male, right? So we took away man, so it's like, also, but prince is closer over here. Sovereign, oh, I love that. Sovereign, ruler, that's king with man removed, right? Fantastic, okay. Woman is over here. Now I'm going to add woman to this sovereign, and I'm here. What word is close to here? Now it's queen. So when you have a semantic space, when we've gotten to this point where we can actually start with the token encoding and we put it into the semantic space, now we're cooking. Now we're cooking because now we can do math on the ideas. Quite literally. I just subtracted man from king. I could take average. I could multiply things. If I want to have something that's more king than king, sure, I can multiply that. I can force that further out. So now you have a space where you can actually do meaningful things with the words. But we have a problem. Sometimes king doesn't mean king. How many people here have played checkers? Great. What does it mean when I say king me? So I've gotten to the end of the board, right? And then king me means put another piece of my color on top of me, and now I have a super piece, right? Doesn't have a whole lot to do with king here. So it's the same token, but it's supposed to have a different meaning. It's probably way over here. What determines whether I mean king as in I am the king of the world, or king as in I'm playing checkers? How do I tell whether it's one or the other? Context. Because you just heard me say it, right? I just gave it to you. I'm the king of the world means king, as we were just talking about. King me, I'm playing checkers. The context tells you where you are. So coming up with a semantic space is not enough, because words, tokens, need to be influenced by the other tokens in the context. If you don't take into account all the words in the context to inform what you mean by this one token, you're not getting the full story. So it turns out that this was the key innovation that made all the difference and allowed us to build a general purpose learner. And the way that you do this, what we call this is attention. So in attention, what happens is a particular token, king, is now compared to all the other tokens in that context. I am the king of the world. And then what happens is you do some math on that. You figure out which of these are most closest. So in all those words, so you have king and I am the king of the world. What word do you think is closest in meaning or in context to king? I am the. Actually, the actually helps a lot, doesn't it? Because that means that it's a noun, right? The king of the world. So the and world. So that means that I need to combine the meaning of my token king with those two words. I need to move them closer. What's one way, those of you who are more familiar with vectors, what's one way that you can move something in a direction? So I have three vectors. I want to move this vector closer to where these other two vectors are. What do I do? What mathematical operation? Simpler. Oh, so transform matrix, absolutely right. Even simpler. Subtraction, almost. How about take the average? Did you say average? I didn't hear you. I'm sorry. You get credit. Okay. So average. As a matter of fact, that's the trick. So you actually taking the average of the things that are most important. Matter of fact, for the ones that are most important, we probably want to take a weighted average. So the is pretty important. World is a little bit less important. So we're going to take a weighted average, and that's going to move that representation of king over just a little bit. That's attention. Attention is using the embeddings for the tokens that we have come up with and influencing where those tokens are in this embedding space by choosing words that are important to it. So now things begin to change. So think about king, we're over a king, and here I said, king me. So I'm going to wipe the floor with you in checkers, king me. All right, now, the things that are very important there are checkers and me, king me. So now when you do the average here, that's going to move all the way over here. Over here is verbs, because now this is much more verb-like, and games, and status in games, and power of the piece. So it moves because you're literally doing math, and now you're moving it to another location. So this is, in this way, we move from words to simple numbers to a rich representation, the semantic space, using attention. Notice the 3 dots there. What do the 3 dots here mean? Could be sequence. Yeah. Even something's missing, right? They left something out. And actually what this means here is we have multiples of these. So it turns out that part of the trick here is each of those stacks has attention that allows us to move around, and it also has what's called a feed-forward network. This is one of those artificial neural nets that I was mentioning before. Each one of these stacks, each one of those blocks, has some of that memory, of that representation. And it can add to the representation because it knows about King Me, and so it knows that it's going to imbue this with more meaning having to do with game and winning and goal. So that's in one of those little stacks. So what do? We do that again. Because now things have moved, right? Now King Me is over here. Me has moved. In this case, when I say I am the king of the world, now king has moved. World has moved. So everything shifted just a little bit. So what do? Now we do attention again. And see where it moves, shifts a little bit more, and then shifts a little bit more. So in decoder stack, one of the things that you need to decide when you're building a generative AI model, and again, this is a transformer model, is how many stacks are you going to have? How much are you going to let it go on? You also have to decide things like how many of these artificial neurons do you want to have in there? And that determines in part the capability of the model. And then we do it again and again until we are happy with where we've gotten. Well, actually, it's a set number, and it can be anywhere from just a few up to 6, 10, even more. So now we're in this, we have this re-representation of our context, and the trick we play is, if there were to be a next word, what might it be? So this is what the model is doing. Now that it's at the very end, it is giving you a probability distribution over the set of all possible tokens. Poof. We know what tokens are. Tokens are words or subwords. Cat, 42, dog, 49, or subwords. We actually know what probabilities are, right? So this is not a certainty. This is not that the next word, so let's go and say, I am the king of the. Well, the highest probability, because the model has probably been trained on this, is world. But it could also be castle. It could be this house, So it could be all of those things, but probably the highest probability is going to be world. So let's say that let's say the model assigns that one like a probability of like 0.8, 80%. And this, for this house, might be lower, like 20%. But all the different tokens, because there are a limited number of them, all have a probability on them, and then what you do is you choose one. You could choose the highest probability one, but that's usually not exactly what you do. You might choose, there are a number of different ways. If you choose the highest probability one, it turns out the model is dull and repetitive. So you often actually want to mix things up a little bit and choose one that's not exactly the obvious choice. But you choose one. So let's say that instead of choosing world, I am the king of the world, instead I chose this. I am the king of this and then we rerun it. And say now, given I am the king of this, what is the next most probable? And you run through exactly what we just talked about before. So this is what's meant by an autoregressive model, and this is how you move from words to numbers to vectors that are moving around because of attention to predicting the next word. I'm going to pause here for just a moment. What questions do you have so far before we start diving more into transformer models? And by the way, this is my tea. And I will drink my tea at various times. And what it means is I'm giving you plenty of time to ask a question and to raise your hand. So don't feel rushed. Yes. And we'll get the microphone over to you, and then we'll get the microphone over to you.
Can you stand up? Yeah. Oh, sure. Yeah, you could.
Is it called decoder stack cycles, the compute cycle? Can you run through some pros and cons about why you would choose more or less cycles and what that involves?
So and just to be precise, you can choose how many stacks you want to have, and it's a preset. Think of it like a loop. You're going to have, if you define it with 3, you got 3. If you're going to define it with 6, that's your architecture that you defined beforehand, and then you're stuck with it. Cons, it takes longer to run. It takes more compute, takes more energy. Pros, it can know more and do more. The more stacks that it has, the more reasoning it can do, and the more subtle the reasoning can be. Plus, literally it can know more, because remember, in each one of those stacks, you have what's called attention, and properly self-attention. That just means each embedding for each token is moving everything else, self-attention. They're moving each other around. And you also have that feed-forward network. So that's where knowledge is represented. And as you have more of those stacks, you have more ability to do that. But it can get huge. So at inference time, when we're actually running these and we're asking questions of the model, it takes longer to run. And to train it, boy, training these models is where the real cost comes in. That gets expensive, and the bigger the model is, the more stacks you have, the more expensive and intensive that training needs to be. Question?
We have a question online. Where is all of this computer power housed? Are there specific servers or locations that are the common denominator, allowing all of these calculations around the world?
Excellent question. So when we started this, we thought that the only models that would be any good would be enormous. So let's take a quick show of hands. GPT-3, okay? We know it's not the greatest model, but it's okay. And we have these artificial neural nets in here. And for each node, you have connections. So these are parameters. So it's going to take a couple of parameters to define each one of these, and then the connections between them. So in a small network, you might have a couple of hundred parameters. That's really small. But if you have a larger one, it might be a couple of thousand, hundreds of thousands. How many parameters do you think GPT 3.5 has, the simpler of the models? How many people say, let's start big, 100,000? 100,000 parameters. You think more? Okay. Million. How many people say the million parameters? You're going to have to vote for it. Gonna have to vote for one of these. Okay, million. Okay. Let's go higher then, because I don't have a whole lot of hands here. 10 million. How many people say 10 million? Okay, good. Let's go higher. Not everybody's voted yet. 100 million. 100 million? Okay, all right. Billion. A few, okay. 10 billion? 100 billion? How about 175 billion parameters for ChatGPT 3.5? Enormous. So the initial models that we had in order to get these types of capabilities, so we thought, needed to be this large, and so they could represent that knowledge and do that work. And this requires enormous resources. That is not going to fit on your PC. That is not even going to fit on your very high-powered desktop. It's not even going to fit on just a regular server. This requires specialized hardware where all of the GPUs, graphics processing units, are tied together to make one virtual, enormous, high-speed machine, energy-intensive, and was very difficult to train. And that's why the initial models that were capable were the province of only the large tech companies that owned the computers or could lease the time on the computers to do this, because this was an endeavor costing millions of dollars to train one of these models. Inference time is a little bit different. When you're actually just running it, you're not training. You're not training the model, and we're going to talk about training in just a moment. Instead, what's happening, you're simply running it. Give me the next word. Okay, next token, right? All right, now that I have next token, let me start over again. Give me the next token. So still kind of expensive, but not nearly as expensive as training the models. But as you're going to find out this afternoon, we've discovered that you don't need to train, the models do not need to be as large. What was happening was that they were under-trained. So it turns out that you can get something that has about GPT-3 performance with only 7 billion parameters. So instead of 175 billion, you have 7 billion, still a lot, still a billion, but much, much smaller. And what was happening? We were under-training. We weren't giving it enough information. It turns out that in these stacks, in these feed-forward networks, they did not have to be enormous to do this, but they needed to have significant training. Plus, we needed to be smarter about how we were training. So, the answer is, originally, only the largest computers could actually train these. Now, it does require significant size to train the models, but not nearly as much as was required before. And there is good news. And that is, you don't have to start over from scratch when you want to train a model. You can take a pre-trained model that has already learned English and maybe several other languages, but maybe it doesn't know about your particular area. Maybe it doesn't know medieval French. All right, give it additional training. And it turns out that there are methods that we're going to be talking about this afternoon that are very efficient. They're called parameter-efficient methods, meaning you don't have to train all 7 billion parameters. Turns out you can train a subset and have the model still learn and still do well. And that's what we're going to talk about this afternoon. Other questions? Yes. And we'll get the microphone over to you.
I use ChatGPT very frequently for my work, and I was just curious, and you already kind of answered it. I want to make sure that I understand it correctly. So ChatGPT currently is not simultaneously retrained or using web information, or is it? That's my first question. So whether this process is kind of ongoing.
Right.
Because when I ask about certain things, actually, for example, in a Python package, there's been some revisions, and it's not so good with that. If there has been some updates in the last year or so, it just doesn't know, and I have to exactly feed in, yeah.
Let me pause and answer that one first. That's a great question. So the world knowledge that the model has is absolutely determined by when it was trained. You're absolutely right. And this is not something which is just easily updated. This is not a database, right? It's not storing it in a table where you can just update. Instead, this is, you saw all the hand waving I was doing up here. I have points all over the place. They're influencing each other. This is all stored in the deep neural net in a way that is not directly accessible. So how do you train it? We're going to be talking about it a little bit, but you update its knowledge by giving it additional training. But we just talked about it being expensive. And ChatGPT in particular, 175 billion parameters, that is no, these are not pennies, right, to update that model. So smaller models are easier to update. But keep this in mind. I'm going to ask you if there's another way. You cited the problem where you wanted to do some programming because these models know languages. Computer programming languages are languages. They know how to program because train them on programming languages. But sometimes new libraries come out. Libraries are collections of code that do things for you, and they get updated all the time. And the model won't know about it. So how do you update the model and so it knows about it? So remind me of that, because one way is to train the model, but there's another way too. Did you have a second question?
Good to know, thank you. And something very related. So I'm always curious whether, as an individual user, it also remembers information, user information from me or not, because I sign in using my own account. Let's say there was an issue and it prompts, sometimes it takes several prompts to get to a point where it can really provide accurate information. That's something I haven't tested myself, so I think the answer is no, it's probably not learning from it. So
that's right.
Maybe that's a feature that will be added later on, I'm not sure, but I wanted to ask about that aspect, yeah, personalization.
So we've just heard that training is intensive and expensive and not something you can just do at the drop of a hat. You're absolutely right. This is not ongoing training that the model is doing. It's inferencing. It is simply going forward, predicting the next word. What happens when you get to the end or when you end the chat? It's gone. They're saving the text. Unless you explicitly have an agreement where the text is not saved, the prompts and what comes out is not saved. It is being saved, perhaps for training at some later point, but not being used to improve the model real-time online. That's not going to be happening. And this turns out to be a problem because we expect the model sort of might know us when we use it for a while. So what do? Remember the context, right? So one way is that off to the side, maybe you've stored someplace a paragraph about yourself, your preferences, who you are. And this is sometimes called the system prompt. So you put information that you always want just prepended no matter what, who you are. So I have one that says I'm the chief data scientist at a data science institute. Gives me my background a little bit, and so it knows how to pitch things to me. This can result in funny responses, because I will often ask it to explain things to me like I'm a 5-year-old, because I want to figure out how to best express it. And so it'll explain to me, but then it will add, like, which you should be familiar with since you are the chief data scientist. And I'm like, yeah. So, but that uses up context, right? So that's something which is important to keep in mind. The model itself is not going to be updated, but you can absolutely store some information in the context. We'll do question here and then question over here.
Is that model that automatically updates live real time? Is that kind of the next leap in AI that we're waiting for at least for the generative models like this?
There are very interesting developments, and we'll be talking about those, but the instantaneous training of the models in their current form is not something that's easily done. But I draw your attention to the context again. So it turns out context is going to be key. And then also be talking about a new type of learning called in-context learning that we'll talk about at the end. But no, I don't think the models themselves are going to be easily real-time updated, not the weights, but there may be a way to get closer to that.
We have another question from online. Who is responsible for training the models with social norms? Should that person be held accountable if they provide biased information? And are the models trained to shift social norms when interacting with different cultures?
I get so excited these are such great questions. Okay. What was the model trained on? What did the model learn from? Us. And what we've written on the internet. And articles and lots of different places, but yeah. Any issues you might think of that might come up? Yes. So the models hold up to us an unforgiving mirror of who we are and how we have thought and what we've written. So absent any other work, you're going to get responses from this that are typical that you would expect in exchanges that you might find in literature, but there are a lot of exchanges from the internet. So imagine, and you all, those of you that have worked with ChatGPT before, know that the way to sort of get a better response is when it gives you a response and gets around to producing it, and you say, that's not exactly what I meant. I don't think you're right about that. And what the model does is says, I'm sorry, right? And then it tries again. Let's pretend you're on the internet. Someone says something and you say, I don't think you're right about that. Do they say, I'm sorry? No. They might start by making comments about your mother, for example, right? I mean, that's what happens. So absent any additional training, the models are going to be like that. So there has to be some steering of the models, and so it is helpful and not harmful. And then we may want to steer it away from certain topics as well. We may not want it to be able to tell you how to build an explosive device, for example. But now this raises a whole host of other questions. Whose guidance? What guidance? One of the interesting things about Claude 3 that was announced yesterday was that part of the big announcement was the model is far more capable, it's even better at writing code. It can have context links that are much longer, all these great things. But one of the big things that it mentioned is we also have modified the alignment. And so it will not refuse as much as Claude 2. So Claude comes from a company called Anthropic. Anthropic, these employees were part of OpenAI. How many people have heard of OpenAI? Yeah, this is the trainers, the makers of ChatGPT and GPT-4. Anthropic folks said, you all are not doing enough for safety. And so they broke off and formed their own company, which then OpenAI promptly invested in because it's companies, man. So they invested in, and then Anthropic instituted something they called constitutional AI. We're deeply embedded in these weights. From early on, it was steered to respond in a way that was helpful and not harmful. It was very rigorous training. So much so that there are certain conversations that you cannot have with Claude 2. One of the research projects that we took on was around the French Revolution. So at the Data Science Institute, every semester we take on anywhere from 4 to 6 research engagements. Our data scientists and our master's students work with researchers here. We've had projects with a number of you all here. We actually put together undergraduates and put together a team, and they solve problems often using AI. And one of them was to work with Professor Holly Tucker, who runs this wonderful course of the French Revolution that you learn about through gameplay. It's like Dungeons and Dragons for the French Revolution, and it happens over the entire semester. And one of the things that you can do, you argue. You try to make your case, and sometimes the king gets to live, sometimes, all sorts of different possible outcomes. But sometimes people want to do things like write to people that are outside of the game. Those of you that are gamers know about non-player characters, right? NPCs. So maybe you want to write to George Washington and say, George Washington, we stood with you when it mattered. Now we call upon you. And maybe if you have a convincing enough argument, maybe he's going to send money or, weapons or people. Could. It's a game. And this works really well for GPT-4, and we tried it with Claude. And Claude said, no. This involves violence, and it involves the procurement of weapons. This is not an allowable conversation. And we're like, it's the French Revolution. It already happened. This is history. We're asking you to play a character. No. We could not use Claude 2 to do this at all, which also meant that you can't engage educationally with it to actually learn about the French Revolution because there was violence during the French Revolution. So, alignment and what's called reinforcement learning from human feedback or from AI feedback, guiding these models, and so they're not just trolls on the internet, involves some very important choices. And you can go too far, or you can go not far enough. Depends on what values you hold. And if you own the model, it's possible for you to decide and to not have external input on what is the proper direction to go with the models. That's why it's very important to have open source models so we can understand what's happening and so we can actually have multiple avenues to explore these models. So that's a great, great question. Other questions? And yes, we'll get the microphone over to you. Right up here? Oh, right here first? I'm sorry. Yeah, we'll do that. Yes.
Hi, Professor. My question is on the training. I'll use a sports analogy. If you got change athlete's jump shot or a batter's swing or a boxer to southpaw, it's a lot of training to change them to do that. And there's been proven biases, especially in imaging and facial recognition with these models. How much is the training weighted on the people that are in these firms at OpenAI as opposed to the customers? Because we know if you go to hiring practices in Silicon Valley, there's less than 2%, there's 1.5% black people that's in there. So like when you're talking about imaging biases and stuff like that, how much is it the consumer that's using it, that's able to train these models as opposed to the people that's at OpenAI or at Claude or Gemini or et cetera?
Great, great question. So sort of so much in there. So one is, what are the guidelines that you might use, right? So even how might you steer it? And who participates in that decision making? So that's one thing. But there's an even deeper issue, perhaps insidious, might characterize it that way. Remember that what we said here was that the model training takes place, and most of the learning is taking place in the stacks here. So what were the two parts that we had here? We had the part that did the averaging, the sort of what was that called? Attention. That was called attention. That's right. Attention or self-attention. So that's one thing which is in the stacks. What was the other thing in the stack? This was the part that did the actual learning and the representation. Yeah, so this was artificial neural net here. This was the feed-forward net. This is the enormous part. And remember, this is a complex representation. It's not a database, right? And so its learning is distributed across all of these nodes. It is not something where you can just pull something out. So when we do alignment with the models, what we're doing is guiding. We'll say, when you get into this neighborhood, go in this direction rather than this direction. Did I fundamentally change and remove things from these stacks when I do that? No. Instead, what I'm doing is I'm guiding the network. I'm giving it guidance on where to go. All that is still there. So this is putting a gloss over what the model has learned. So anything that it has learned that involves a bias or a misrepresentation, all of that is there still. But you can guide it, and so it's not as apparent, but it's very important for us to remember that it learned from us. And this is why I call this the uncomfortable mirror being held up. Those representations are still there and cannot be removed. So the choices that we have are to curate the data that goes in, But then we have the same issue. So curating data is important. Knowing what goes into the training is important. That's also where the open source models come in to be very important. And not all open source models are equal, because sometimes they'll open source the architecture, but not the data that was used to train it, which means we don't know what it learned. Some models just recently open source everything. Here's everything that we trained on, and here's the architecture. Then you can get a better sense of what the model has learned and what it's representing. So, the issue of alignment and what you align is huge. And keep in mind that often when we're doing alignment, we're doing it from our perspective. It turns out that there are huge issues in languages which are not as widely spoken, where, issues that can lead to violence that we're simply not aware of. We don't know that this use of this particular phrase is an absolute slander, right? And so we don't align against that. We just align the things against the things that we are aware of. So there is no easy, set, existing solution, but even just knowing about this means that you can engage with it and begin to explore solutions. And I know that's an awfully unsatisfactory answer, but it's the beginning of an answer. Next question. And let's talk more over lunch. We're going to take a break in just a moment, but we'll take one more final question.
Thank you, Professor. I have a question more about the proliferations of those models. Copilot, Meta AI, ChatGPT. When you were mentioning some of them, is there kind of a father of all of those models based on those subsets you explained? So do we have kind of a root model and all those different ChatGPT-like copilots? Exactly. Okay, that's the tree. So it means that you have it. That's what I was wondering. Yeah, thanks.
So let's go and we'll take a quick look at the tree, and then we will stop for some coffee, and then I'd love to continue these conversations. So what you're looking at here is from the earliest days, and it was around 2018 that the paper "Attention Is All You Need" came out. And what we had before then was things like fast text, word-to-vec, glove. When I talked about the embeddings before, this is king minus man. Those are those embeddings. That's where they first came from, but there was no attention. King was here. No matter what, king is here. I don't know about the other meanings of king, just this one. And so they were deficient in that way. Still better than nothing. Then we have different models that grew out of that. And it turns out that all of these are transformer models. So they all involve attention and the stacks, which have the attention and also the feed-forward network. That's the secret sauce for all of this. But the decoder one, which is the generative model, its job is to produce the next token. Those are called decoder models. All of generative AI are types of decoder models. A whole bunch of those, and we'll talk about that. But there also are other ones as well, which are not as widely used right now. They do slightly different things, but they also use attention and feed-forward networks. We have workshops. Would love to have you join us for workshops to talk more about those. But here we'll talk about the decoder. So it turns out that really with all of these models, the architecture is not all that different. It's kind of what you were looking at before. It all does token encoding and then token embedding, and then it does the stacks, and then it does next word prediction. But what's different about most of these is a little bit of the architecture, how big they are, how big is your feed forward, how many of the stacks do you have, but primarily the training. So think about it. If you have trained a model and the only thing that it knows to do is to produce the next token, those conversations are going to be pretty boring, right? So let's say I'm a fan of Stephen King, and I would like to know some of Stephen King's books. If I were to put that in ChatGPT, what comes out? Yeah, that says, certainly. Stephen King is a prolific writer. Here are some of his books. But if you put that into GPT-3 right here, hi, I'm a fan of Stephen King, and I would like to know some of his books. What does GPT-3 respond? Because he is a good writer, and I would like to be able to read more of his books. So instead of answering my question, it continued my question. And I can't help but get this. Whenever I interact with a model that has not been further trained to be a chat model, it always reminds me of smart dogs versus dumb dogs. Most dogs. So with most dogs, when you point to something, they look at your hand, right? They're like, look over there. And it's like, I'm looking at the hand. I'm not. But really smart dogs, when you point to something, they'll go, what? So they know. With these models, with the untrained models that have only been trained on the next word prediction, all it knows is, I got to continue this sentence. I've got to continue I've got to produce the next word. So how do you get from GPT-3 to a little bit further up there, ChatGPT? More training. Whenever you see something that ends with a question mark, or whenever you have this, then the proper thing to do is to answer the question. Shift, answer the question. And these are powerful general purpose learners. So as you give it more and more examples of conversations, of question and answer, it learns how to represent questions and to recognize questions and to know when a question is asked, you don't continue the question, you answer the question. So these models, primarily, what drives many of the differences here is the training that they've received. This is what we're going to talk about after the break. How do these models get trained? How do they learn? But for right now, let's go and take a good 10 minutes. We'll get some coffee and snacks, and I'll be down here to answer other questions that you have. Glad that you're here. So now we have the foundational information about what's happening with the models and how they work, high level, but know that everything that we've talked about here is absolutely directionally correct, and if you wish to go deeper, you absolutely can. Matter of fact, a little bit, I'm gonna put some pseudocode in front of you so you can actually see the entirety of a transformer decoder algorithm. But first let's talk about, let's remind ourselves of what the task is and what the model is doing. So recall that we have context that we put in. That context is turned into numbers, and then is turned into embeddings, then is fed into the stacks, and then is used to produce the next token, the response. And you simply wrap it and go again and again until you have a full response. So in this case, see if you can guess what this next word is. Beware, for I am fearless, and therefore, what do you think it might be? You can call it out, and then I'll repeat it. Brave. Okay, good. I like brave. What else do we have? Dangerous. Okay. What else? Naive. What other words? Invincible. Okay. Word is powerful. So notice what we did there. We saw the context up at a certain point, and then we were using our own biological deep neural net to actually come up with different words and to figure out what the next most likely word might be. And I was giving you feedback too. Right? So I was giving feedback to the room saying, yeah. And then we got to one that was close, and we had invincible, and that was the closest. So I was able to give you feedback and say, the word that you have is far away versus, the word that you have is pretty close. So I could give you feedback. And very quickly you could arrive at what that correct word was. So it turns out that this is actually the task that we use to train these models. Dead simple. But it turned out to be one of what I consider to be the three revolutionary changes. One of them, us having a powerful general purpose learner, this idea of a model with attention. Second, being the idea that to train these models, rather than having labeled data, which is how we used to do this all the time, you'd have to have millions of examples of labeled data to train these models. Instead, all we got to do is leave stuff out. Leave out the last word. Tell the model how close it got. So it's called self-supervised learning. And it allows us to turn any information that we have into training data. I have text, great. I can leave out the last word, train the model to guess the last word. That's how you train generative AI. And you can actually, anything where there's information, we're going to see that this also holds for multimodal models. You want to learn pictures? Great. You have a powerful general purpose learning algorithm. Leave part of the picture out and have it guess the missing part. You want to have a model that learns audio, that learns language, spoken language? Great. We know how to tokenize things, turn it into numbers, train it by leaving things out. That's the core part. Powerful general purpose learner algorithm and self-supervised learning. So we're going to try this out. So this is some of you who've been, I recognize some of you. Some of you have been to some of our workshops or in person. So if you have seen this before, keep the pleasure of knowing what the answer is to yourself, if you would. But if you don't, I'm going to ask you to do the following. I'm going to ask you to be brave, as we were saying a moment ago. Shout out the very first word that comes to mind that should end the sentence that you're going to be seeing in a moment. I want you to do this quickly, and I want the bad answers, because this is actually probing your network. It's as if we did GPT-4 and we said, stop, stop. Where are you right now? Before it has a chance to go through representation and the re-representation and the shifting. I want to stop you and ask you to answer what comes up early. And then we're going to see what you would have to learn, what information must come to bear for you to get to the correct word. So I'm going to flash this sentence up to you. I'm going to ask you to very quickly shout out the word that you think belongs there. We in agreement? No shame? Okay. Here we go. This is Zora Neale Hurston, Their Eyes Were Watching God, the very first sentence in her book. Ships at a distance have every man's wish on blank. Gold. Perfect. Words? Other words? Okay, we have deck. What else? Mermaid. Excellent. Thank you. What else do we have? Home. Pirates. Fantastic. What else do we have? Discovery. Fantastic. Shipwreck. Fantastic. What's that? And real loud. On stop? Pigeon. Oh, okay, sure. So interesting thing here, these are all nouns. How did you know that you needed to be calling out nouns? Yeah, okay, now I'll show this. Okay, so it's got to be, because you weren't thinking this, but this is an object of a prepositional phrase, right? It's got to be a noun, or something that's acting like a noun. All right, so apparently you have to know that to even be in the neighborhood, because there are lots of words, right? And you were at least in the neighborhood of the nouns. Something else was interesting. You all mentioned things that had things to do with ships. Sometimes it was wish. But they all had to do with some of the meaning of the other words. So apparently, in order to be even closer, you have to represent the meanings of the words. You have to know that ships are things you can stand on, that they have a deck. You have to know that with wishes, you might wish on a dream. So wish on dream, if that's the part. So you have to know the semantics of the different elements of the context before you can get closer. Okay. What's more important here? What do I need to pay attention to in this sentence? Ships at a distance have every man's wish on. Do I need to pay attention to wish or to ship? Ship, right? I need to pay attention to the ship. That's something else I need to learn. I need to learn what words are most important in any given phrase. I need to learn what the attention weights need to be. All right. Now that you've had a chance to think about it, what word comes to mind? So we had deck and we have board. Ships at a distance have every man's wish on deck. Ships at a distance have every man's wish on board. How many people like ships at a distance have every man's wish on deck? Okay, great. What appeals to you about this? And let's go ahead and, Damani, if we can, yeah. What appeals to you about every man's, that ships at a distance have every man's wish on?
There's a space after on.
Yeah, okay, yeah, so.
So not on board.
Oh, okay. Okay. So you have it fits in syntactically. Anybody else like on deck a little bit better? Raise your hand if you like on deck a little bit better. Okay, yeah. Why do you, and we'll wait for the microphone to come up. Why do you like ships at a distance have every man's wish on deck? Here you go. Yeah, right here.
Well, because it makes me think of people standing there.
Okay. Standing, so very concrete. Okay, how many people like ships at a distance have every man's wish on board? Raise your hand if you like this one. Okay, great. Damani over here, if we could, like way over here. I know you haven't gotten your steps in, so I'll keep working on it. Yes. So why do you like on board?
I have a confession. I'm a big fan of Zora Neale Hurston.
Me too.
And it sounds like her.
Yes.
To me. And on deck, the D sound there is kind of abrasive. It sort of breaks up the rhythm of the sentence to me.
Fantastic. So a couple of things there. Style of writing. So one of the other things you'll have to know is style of writing. And yeah, Zora Neale Hurston, hell of a writer. And here's writing metaphorically. So on deck. That's concrete, it's harsh. On board. Wishes on board. So ships at a distance have every man's wish on board. Metaphorical. So in addition, all the things that you have to know in order to get this right are parts of speech, the semantics, where to pay attention to in the sentence, style of writing. So this is information that you needed to have and have access to in order to get this word right. Let's flip it around. All those things are learnable. If you have enough examples of you got it right, you got it wrong, or you were close or you were not close, these are things that you could learn over time. Given all the time in the world, you could learn about these things. You may not even know at first what to call it. Style of writing? One sounds harsh, one doesn't sound harsh. For Zora Neale Hurston and for good writers in general, they tend to go for not harsh. And you may learn later, you might learn about metaphorical. So these are all things that are learnable. So think about what we have. We have a powerful general purpose learner in transformers, and in particular in decoder transformers for generative AI. They can learn things if they are given enough opportunity to do so. Now, for training material, we have everything that's ever been written. And we can do this trick where we leave out the last word or leave out a word in the sentence. And the model has the ability to learn what is on offer. And what's on offer? Well, encoded in all of this is the idea of parts of speech, of semantics, of. So by filling in the simple task of filling in the word, you can learn about ships. They float until they don't. They can get trapped in ice. Ships have decks, they have sails. You can talk about being on board, and sometimes when you talk about being on board, it's two different words. You're on board versus on board. I am on board, which is a little bit different and isn't necessarily about a ship. These are all things that are learnable with enough training material. So how much training material? Well, early on, these models would be trained on thousands, tens of thousands of documents. If you want to think in terms of tokens, millions of tokens. And Charo, is that about right? Millions of tokens for BERT? I think it was millions. Yeah, in that neighborhood. So not a whole ton. But then we upped it to billions, much more text. The most recent models are trained on trillions of tokens. Trillions. Significant compute, but again, remember, the models don't have to be as large. What's important is that they have trillions. So now the most recent model, open source model from Google called Gemma, which we're going to be talking about later on this afternoon, was a 7 billion parameter model. So it can run on a beefy laptop. You can train it on a very beefy laptop. But it's been trained on 6 billion tokens because we found that the more training, even the smaller models benefit from that type of training. So what does that look like? So here we go. We ask it to guess the next word. It says shore. That is wrong. So through a process that's called backpropagation, parameters are modified. I'm going to give a quick overview of this so you can get an idea of what this is like. The decoder stack, that feed-forward network, all of the weights of the nodes where that information is represented, all of those are parameters. Parameters are things that can be learned, can be modified. They're all numbers. The attention and the decisions that we have about the attention mechanisms, where they attend to, how they actually do that mapping, also parameters, also learnable. All the way back to the very beginning, the token embeds. How do we decide where to put king? Its position, all of those numbers, that vector of where it is, parameters, learnable. So where does all this come from? The training. Now you can get an idea of why we need trillions of tokens to train this, because it is learning everything. It starts with random, and then you get told you did this, got it wrong. What backpropagation does is determines which parameters were most responsible for the incorrect answer. You gave me bad advice. I'm not listening to you as much anymore. When I see this kind of thing again, you're downweighted because you led to the wrong answer. And then you work your way backwards. And all the influences that led to the wrong answer get moved in the other direction. And it's using something that's called gradient descent. This is where the calculus comes into the game. I've been secretly talking to you about linear algebra, just so you know. But this is backpropagation, and you actually then can learn on it. What's most important to take home from is that this is not a guided process by us. Instead, this is a word that we have. It was wrong. Therefore, we're going to move away from that, and we're going to try again. Deck, closer. Matter of fact, deck is close to the right answer. Deck is here. Board is here. So it's not quite so wrong, but we're still going to do backprop because not quite. I need to be nudged. So I'm going to backprop a little bit more. And then when I run and I get the right answer, I don't do any learning. So universal truth, right? You don't learn from getting things right. You learn from mistakes. Kind of a life lesson in there. So you learn best from mistakes. Models are exactly the same thing. Am I telling it exactly what to learn? No. I don't say, hey, now pay attention to parts of speech. Instead, what I'm doing is I'm saying, here is signal in the form of words, represent however works. Now, because it's a large language model and it's actually representing words, you can go and it can actually begin to identify writing style. And so now actually you can have a conversation with it about writing style. Why? Because it's had to learn about that, plus it's a large language model, which means it can produce text around things. So it's this interesting convergence of having learned about text and then also being able to use text to describe and to draw on what it's learned. That's a large language model. Let me pause here. What questions do you have about training of these models?
One more question on the back propagation, because we talked about this on like the second day of class about context and more geolocation. So the same way you did Zora Neale Hurston, I made a sentence that I was in London visiting the BBC in Leicester Square, and my meeting was on the 14th floor, so I took the blank, and it keeps saying elevator. Even if, I know you told me like use gray skies, use gray, G-R-E-Y, so the A-Y. Everything I'm saying about London and everything else, it says the elevator. And when I keep training it and back propagating to say lift, then if I ask it, oh, I went to a meeting and ran on the 3rd floor, my leg was hurting, so I took the what? Then I was saying lift for ran. So how do you, like, why doesn't it get the context of location to speak to what a different community would say, like lift or tube instead of subway or elevator? Like, why is it not getting that context when in its writing?
So let's think about the task that we have here and what it has to go on. So if you said, I went to Rand and then took the blank to the 3rd floor, if it doesn't know that Rand is at Vanderbilt University and Vanderbilt University is in the US, then it's going to say elevator, absolutely. If you were to give it more context of saying, and this could be in the system prompt, or this could be more information, to make it clear that you're in the US, it might more likely say elevator. But if you're in Leicester Square, then it might say lift, but only if the model has been trained enough on that text. And so this is where the importance of knowing what the model has been trained on is so important. Does it even represent, a different culture, and different word usage in a different culture? If you don't know what a model has been trained on, you don't know if it does. And so the only thing that you can do, and what's incumbent upon us, is then to do the testing to see how good that world knowledge is in that particular domain. And if it's not, then we can do additional training on it, but know that it may be deficient in that. So if you're working with a closed model, you've got to probe. If you're working with a closed model, you've got to determine whether it has sufficient training in the area that you're interacting with. That being said, keep in mind that context window, because that context can play an important part. Other questions?
We have another question online.
Yes.
Which I will paraphrase. Ishwar, please correct me if I'm wrong. This question is asking, during backpropagation, if the weights are overtrained and cause overfit, will they be penalized? And then they put a caveat other than by regularization.
Okay. Someone who knows their machine learning. So what we have going for us is, because we have very few controls over what's happening, is it's having to learn an immense amount of information. An immense amount. Yes, the models are huge, but think of 6 trillion tokens. That is everything that's written that's available electronically. So the idea of overfitting, and the idea of overfitting is that the model learns something so well that it doesn't generalize anymore because it knows, and it's just memorizing. It's only memorizing and therefore can't generalize at all anymore. But actually, it turns out if you have that much training data, it is impossible to generalize, to overfit in the sense of that the model hasn't learned anything useful. However, it does memorize some things. This is something which is becoming more apparent now. Think about how you tell, and the greatest example of this right now, or the most concerning for many folks, is computer programming. How do you tell whether a model is good at computer programming? Well, you give it a programming test. You give it a description of what it needs to program and see if it writes a correct program. Are those tests on the internet? Yep. Someplace. So if you pull a test off of the internet and then test the model, and it's been heavily trained, it's going to say, I know that one. And here's the answer. So it can turn out that the models appear to be very, very good at math, at law school questions, at programming, but what could be happening is that the model is just memorizing. So, one clever approach recently promoted is, for math, for example, don't pull stuff off, come up with a functional equivalent, and so you change the numbers a little bit. If you know, if you've memorized what 13 times 12 is, then I could ask you what's 13 times 11, or 13 times 13. Change it a little bit, and it's no longer, memorization doesn't help you anymore. So the model can generalize, and when you do see some models definitely taking a hit when you actually modify what it's being shown. And so it's a more true test of something it's never seen before. But other models are much more robust to that. But that's something that also we need to be careful about. Let me take one more question, and then we'll get to, okay, yes, and then we'll.
My question was actually pretty similar. I know in a lot of machine learning, you have a problem with, you talked about undertraining, overtraining.
Yeah.
But I was curious, does that even apply to large language models?
So does undertraining still apply? It does, actually.
Well, overtraining.
And yeah, so undertraining definitely does, because then we realize that there's more gas in the tank. Even with that 7 billion parameter model, there was a lot more it could learn if we simply gave it more training. Overtraining, in this sense, where we're beginning to train on the materials that we're trying to test on, but for that, there are ways around that. Overtraining in that it's not actually representing things. It does generalize. It's not just repeating. So often, one argument that you have, or one critique of the models is, it's not doing anything. It's simply repeating things that it has seen. Not true. And obviously, we have novel things that we put in all the time. And it does provide other types of responses, but not entirely incorrect, because it can memorize things. And in evaluations, we have to be sure that we're not just probing that. Now let me take take you a little bit further into the theory. One critique is that all that's happening here, you put in the context, and then you produce something else, it's all probabilities. It's all distributions. Therefore, it hasn't learned anything at all. It's all distributions. I'd like to suggest that you flip that and keep the following in mind. Distributions are information. Distributions carry information. So we may turn the words into numbers and then into vectors, and then we may actually train it, and so it comes up with a probability distribution. Remember, board had like 80%, deck had like 40%. That distribution is representing world knowledge, which is stored in here. And when you follow a particular path, you're actually unfolding information. So yes, it is just producing a probability over the next word. But distributions are information. So it's not actually a knock on the model to say that it's entirely a probabilistic model, because yes, it's representing information. Now let's talk about where we are here when we're decoding and we're choosing which word to choose next. Somebody during break mentioned in the Vanderbilt AI interface, which is an interface in front of these generative models, which has some really cool tools, and we'll be talking about those a little bit. There's a slider bar that starts at 0.5. So somebody tell me what happens when you turn the slider bar all the way up to 1. What do you get? What does it look like? And you can just shout it out, and then I'll repeat it. Sort of random, creative, kind of, but kind of random. So what's happening there is you're turning up the temperature. So here you have a probability distribution over all the next tokens, right? If you turn that setting up to 1, you're turning up the temperature, which means, wow, I might choose any one of these. There are many different paths that I could follow, and one is much more as just as likely as the other now. So now I can walk in a very different direction. This means it may be less guided by the context. It may be less guided by the knowledge in here, which means it could make things up. It can get more creative. Okay? Now let's turn that slider bar all the way down to 0. So the model is going to choose the next word, which is most likely, which might be We use ums a lot. We repeat ourselves again and again and again, and that's how we talk, and sometimes that's how we write. So often what will happen if you turn the temperature all the way down is the model will repeat itself, tell you what it just said, have filler. In other words, dull, less informative, and less information coming from the model. So between the 0 and the full-on 1 may be the sweet spot that you want to have. But you have some control over how creative. But keep in mind, really what's going on is the temperature setting and how you're going to be treating these probabilities of the next token. Are the probabilities going to carry all the weight? You are choosing only the most common, the most highest probability word all the time? Great. 0. Want to be highly creative? Turn up the temperature all the way? Boy, lots of different places you could go. It's still probably be a noun that you would choose, but you can go in lots of different directions. But know that it's going to be less bound by the context and by the learning of the model. Everything the model knows is through training. So we start with GPT, and that's the dog looking at your hand, right? This is the model that simply produces the next word, and that's all that's doing. It doesn't know about instruction following. It doesn't know about texts. It simply knows it needs to produce the next word. So you can give the model additional training, and it's called instruction fine-tuning, IFT. And this is giving it examples of questions and answers. So think about the model. The model is a general purpose learner, and it begins to form representations of tasks, problems, questions and answers. Given this kind of a problem, approach in this way. That's additional training done exactly the same way that we were just talking about. So it's exactly the same thing, but what's different is what you're training it on now. So now what you're training it on is maybe as a context you give it a full question. And then on the testing you see if it produces something close to the answer. And so then begin, through backpropagation, to change those weights. And so the model gets better at recognizing and answering questions, at recognizing and following tasks. That's instruction fine-tuning. Now at this point, if you said, I'm interested in reading some books by Stephen King. What are some books? The Stand, Carrie, and I could go on for a long time. He's written a lot of books. But that's what you're going to get. It's not a chat, right? This is not being friendly. This is just the answers, because it recognizes you asked a question. It's giving you the answers. Is that what ChatGPT does? Now, it almost never does that, right? It always greets you first, and then gives you an answer, and then maybe even suggests more books. Would you like to hear more books? I've listed the first 400 books by Stephen King. Are there additional books you would like to know, right? Well, it turns out that's additional training as well. And that's previously reinforcement learning from human feedback. This is a little bit different. It looks a little bit different from backpropagation, but the idea is that you're changing those parameters. And this looks like, here's a whole answer, here's a whole answer. Humans say, I like this one better. This is where alignment comes in. So with this approach, you can say, I prefer this answer, which is more helpful. I prefer this answer because it's less harmful. That's where the alignment and the preferences come in, and then you can begin to steer the model on these high, very high-level concepts of what it means to be helpful or less biased. But remember, when you do that, you're not changing the internal representations, right? You're guiding how the model is responding. Everything still exists in there. And this is a whole semester, a whole dissertation in ethics around how you choose and what you choose and what you do for alignment. So questions about how we go from a base model all the way up to the chat models. Devani, question right up here.
Hey, how are you providing the feedback at scale?
Mm-hmm.
And what are the sources of the truth of that?
Good catch. So you can't really have a human here, especially for the reinforcement learning from human feedback. All the other stuff, all you need is a huge question bank. Oh, you want to generate more questions through a question bank? How about having GPT-4 do it? You can absolutely do that. I want you to follow the following instructions. I'm going to give you an answer. I want you to give me the question that goes with the answer. And give me 400 of these. Great. Now I can use that to train my smaller model, and so it's instruction fine-tuned. Actually, this is how some of these really good smaller models get trained and how they're able to share out exactly what they've trained on because they've generated the training data. Reinforcement learning feedback is a little bit different because now you're talking about preference. So one way is that you define a model. You have to define a reward model. But you define a model which can't generate the answers, but it can tell which it would prefer. It's a lot easier thing to say, this follows the rules of being helpful, this doesn't. And so sometimes it can be a separate model which you have tuned or given extensive instructions to, and so it knows which to prefer. It starts with humans, and in many cases it starts with humans. This is what I mean, here are some good examples. Generate more, now go through and begin to learn on this. So sometimes it's reinforcement learning from human feedback, then augmented with AI feedback guided by the humans, and then you scale it up to whatever you want. Other questions?
So a lot of what you're talking about is like the traditional machine learning, like you have a question and then you have an answer and then you tell it one thing. But you've also mentioned some things about neural networks and more traditional deep learning where you would say, okay, well, you figure it out. So where does that, do you have both of these at the same time, or like how does the classifications between the two affect a large language model like this?
Let's separate out the tasks. So for those of you who are steeped in machine learning, this is a bit of a sea change for you. Because the task looks familiar. The task sounds like supervised learning. And if you don't know what supervised learning is, don't worry. For a long time, for most of the history when we were talking about AI, we did traditional machine learning. And it really is just in the last couple of years that we've been leaning into self-supervised learning. The tasks are the same, but first of all, we don't have to prepare all the training data. Instead, we leave things out. But the learning, which is occurring, is happening in the deep neural net. There is no random forest that you're training. There is no machine learning model that you're training in the narrow sense. Instead, what is happening is all the backprop. And so the learning that takes place, I'm going to flip forward back to here. The learning that takes place is all through backpropagation. The task is question, answer, but you're learning through backpropagation. And if that doesn't quite land right, we'll chat more during lunch. Yep. Another question.
So backpropagation essentially relies on a difference between the output that was given and the output that is desired. And then that is used to create what's known as gradient, and it propagates that gradient all the way back through one level at a time, and thereby tweaks all the parameters. What is it comparing this to generate, to backpropagate?
Perfect. All right. Ships at a distance have every man's wish on shore. So we get here. I chose, or the model chose, shore. The correct answer was on board. Remember that the model is producing a probability distribution on all tokens, board included. It chose shore, but the correct answer was board. If that probability for board was 0.01, 1%, that's a low probability. That model was very wrong, right? And so that backpropagation then reflects it's very wrong. All right, but let's say you landed on, you chose shore, but board, that was like 0.8. On deck was 0.85, but that was 0.8. That's not so bad. So now backpropagate knowing that you were close.
So it's basing it on its own probability.
It's basing it on its own probability, which is a little bit mind-blowing.
Yeah, it seems like that could lead to pathology.
So the comment was, it seems like that could lead to pathologies. Tautologies and pathology. Okay, yes. Let's talk during lunch. All right. So we have been talking about models and how to train models, but let me ask you some more questions. You've asked enough questions. I'm going to ask you questions. How do I make this model better? How do I make it so the model can learn more? What are some ways that I might be able to do that? So the model is better at doing tasks. So I'm going to repeat that in there, and I'll be able to hear a little bit better.
I just said you could add multiple smaller feedback loops between stages, so you can improve the quality at each step.
So yeah, so one way, and I'm going to stick with the current architecture, but I'm going to modify your answer so I can add more stats, right? Okay, let me be very specific for the machine learning folks. If I keep with the architecture, what choices, other choices can I make within that architecture? Where's the knowledge? Oh, please, go ahead. Oh, yeah, so you can increase the training set size, absolutely. That is one way where you increase the training set and allow it to learn more. Can I change the model a little bit and so it can learn more?
Is there a method to make it quiz itself against the material?
Yes, so actually, yes, that is, there's a way for it to quiz itself, yes. That's where you start getting into the issues, though, because, but what about the model? Where is the knowledge stored here? Where was I saying most of the knowledge is represented in here? Is it in the embeddings? Is it in the... It's in the stacks, right? In what part of the stack? Was it the attention? What was the other part that's in the stack? You have two things, attention and the feed forward. The feed forward is where the representation is. So one thing that you can do with a model that's very small is increase the feed forward network size. So if you increase the feed forward network size, you start from a very small model and get to a larger model, then it can represent more. And we definitely see that. So it just turns out we didn't need to get as big as we got. Right? We didn't need to go to 175 billion parameters. However, if you're at 2 billion parameters, there's a limit to what you can learn and to represent. So what do? Make that feed-forward network larger. And so it has the ability to absorb, represent, and retain more information. So that's one way to improve the performance of the model. That combined with additional training. But let's say you've done that. Your model is the size that it is, it's been well trained, but you want it to do a better job on your task. What are ways that you can get it to do a better job on your task? Yes. Personas, okay. So let me generalize that a little bit. You could give it more context. So think about the programming that we were talking about earlier too. When you described in detail what you wanted to have, then it did a better job. So this kind of makes sense though, right? I mean, the model, given the entire context, produces the next most likely. So if you have something which is really short for the context, it doesn't have much to go on. So yeah, you could always try to have the model be better, but how about a better context? Longer context with more detail. It turns out that is key. Once the models get up to a certain point where they are good at representing, they've been trained on tasks, they've been trained on chat, that's about where you're going to be. So context length becomes very important. Models that you were originally working with, ChatGPT and GPT-4, had context length of about 8,000 tokens. Remember, tokens are words or subwords, so maybe on average like 6,000 words. This is like a couple of typewritten pages, and that's it. So there's only so much describing that you can do. But now, there are longer context models. And this does a couple of things. One, it means you can continue the conversation longer, right? Because remember, when you do and produce the next token, and then you go back, and then you run it again, that's all taking up context length. And as that goes longer and longer, that conversation is taking up more space. And every time it continues and generates the next word, or you ask it something else, that entire thing goes back into the context and runs through again. So it's always growing. So that's why in GPT-4, ChatGPT models, at some point the conversation ends because you've run out of context length. So long context length means you can continue that conversation longer. But it also means you can give it more information in that context. So let's take the problem where, I don't remember what it was now, someone was doing some programming, and you had a library that had not been learned by the model. Remember that? So the model finished the training about 6 months ago. Somebody came up with a brand new, really cool library, which is not in there. Well, if you have 32,000 tokens, you can put the full documentation for that library right in there. So the model may not know about it, but the model has it in the context, the full documentation in the context. Now it can write computer code against that. The model may not know, but if it's in the context, it is aware of it. And remember, when we talk about attention, we've been talking about it abstractly and averaging of vectors, but it means it can attend to everything in the context. If it's writing code, it has immediate access to everything in the context, which means documentation can all be in there. Immediate access to it, which means it can code against it. So more context means that you can absolutely do more things with the model. So the longest GPT-4 model right now is 128,000 tokens. Claude has 200,000 tokens. A week and a half ago, Google announced Gemini 1.5. Gemini 1.5 has 1 million token length. So if the model doesn't know something, now you can put it into the context, reason against it, and then do things with it. And this is not just lookup. So one of the interesting things that Google did was they had a low resource language, not very many speakers of it, but there's a book on the language. And so what they did was, in this 1 million context length, they put the book. Here's a book on a language. And remember, that's just uploading, right? So this is not training. We are not training the model. We're simply putting the book into the context. So here's the entire book in the context. It's all there. It's processing. And then you say, translate this following sentence into this language. The model has never been trained on the language. The model is that the language is a low resource. It's not seen examples of this before. It did not know the language before you uploaded the book. But now it can translate. It can write in the new language. Why? Because it's in the context length. It has full access to all the written knowledge in its context window about the language. In context learning. The model weights are not changing. This is not backprop. But the model is aware of it and can work with it and then can write in the new language and with testing write about the same as a human could if they had read the book and worked with the book. But the speed here is, think about how long it takes to actually upload a document to GPT-4. It's not that long. So this is as close to instantaneous as we can get of the model having new capabilities through in-context learning. So long context windows not only give us the ability to carry on conversations longer, and this addresses the problem that we were talking about before. The model forgets about who you are, what you were talking about. Well, just keep the context window open. You could do that over a long period of time. Or you could give it very detailed context in the form of books, book chapters, articles. Think about you when you're academics here. Think about when you're writing a new grant and you want to have all the other grants that you've put up there before, plus new things you've written, plus some ideas that you have. Now you can have all of that in the context window and begin to reason against that. I'm interested in the following. What if I hadn't done this, I'd done this? Let me think through. Programmers are in the room. Think about having to code against huge code bases where Frank, who'd been at the company for 30 years, has written everything, and you've got to write additional functions against that or new objects against. Well, upload all of the code, all the documentations and all the code. Help me write a program. Help me write some code that'll work with Frank's code. All of this is possible with long context models. So Gemini had 1 million tokens. The next day, in a very fast response, entirely planned, Microsoft released a paper that said, hey, we have a way of increasing the context length of these open source models to 2 million tokens, Google. And now Claude also has announced that Claude 3 can go up to 1 million tokens. And, but not to be outdone, Google had said that they had tested theirs up to 10 million tokens. So this is part of what's coming next. This is part of the new age of very, very rapid acquisition of skills and problem solving within the context window. So the models serve as the basis for this, but the context window is where things can happen. This is why sometimes surprising things work well for prompting. This is called prompt engineering. So has anyone tried the following? Please solve this problem. Tell me the steps you are using to solve this problem. And had the prompt work, and did it work better when you put that in there? So the model worked better when you treated it and you said, tell me your steps. But let's think about this. The model does better with better context. By saying and writing and producing the steps that it's taking on its way to solving the problem, it is creating context that it can operate off of. In actuality, that makes perfect sense. By creating more context, it now has a written record of the reasoning that went into on its way to solving the problem. Just like humans, when we write things down, it's easier for us to solve longer problems because now we have access to everything that we had before. Same thing with the models. That's why prompt engineering, like the personas that you mentioned, ask me questions until you have enough information to do the following. Chain of thought, tell me how you're solving, write out all the steps. That's why all of those things work. Because with better context, you can do more things. What questions do you have about long context and about in-context learning? Oh, and yeah, let's here, and then we'll get there. Yeah.
How precisely, how exactly do you get the context into these learning models? You upload a file. Does that file have to be structured in a certain way, or can it figure it out?
So yes, you do upload. And this is where we're going to be learning about something that's a little bit different from in context. But yes, you load it up, but it actually is all presented to the model. It is all tokenized, embedded, and then it all runs through. To be technically correct, when you do that first, when you put in the context, the entire thing moves as one big bolus through all at once. So the context moves as one object, one large matrix that is multiplied through. So that's actually what's happening. But yeah, so all of that appears and it moves through all at once, and yes, you upload. One thing that I'll point out is that you might think if it's a human, you begin to lose the things in the middle, right? If I gave you a list of objects, you do great on the last few things that I mentioned. You might do a little bit better on the first few things. This is called the recency and previously effects. But the stuff in the middle, you'd be at chance. For these models, the attention, the way that it works is that it is all accessible. And so in tests of the models, one of them is called needle in the haystack, where you insert a particular phrase. It turns out the models have really good access to that if they're engineered correctly. So you don't lose, even if you have a lot of context, you don't lose the specifics. You have equal access to the specifics and to the whole. So question back here.
Yeah, what's the limiting factor on context length? Like, why don't we just set it to 1 trillion tokens? Is it system memory? Is it diminishing returns on the feed-forward network?
So it turns out with attention, if you do it in the raw way, in the most straightforward way, remember, and I kind of said this quickly, every token is compared to every other token. Every embedding is compared to every other embedding, and I do averaging. Well, that is an n-squared operation. The compute and the storage for that grows quadratically. And for those who are programmers here know that's big. So as you don't just grow linearly, as you just add a little bit, it grows with the square. And so you very quickly outstrip the computational resources that you have available. There are other ways to implement it, though, and there's a lot of slightly more recent advances, and so it grows more linearly with that. Then the other challenge, though, is how do we handle distant tokens? So does the fact that I chose this word at the very beginning of the novel, should it influence the last page as much as the words that were the next to the last page? Well, really, we want the words that are closest to have more influence than the ones that are far away. It's not that we don't want to have no influence from the faraway words, but there needs to be good reason for it. So that's the other essential part. And then there's a more particular problem. Be happy to discuss with you. It has to do with positional encoding, but maybe talk over lunch about that. All right. Yeah, one more question, and then I'm going to switch over. Yes.
So one thing that's interesting is it seems like this context is another way of getting knowledge into the system.
Yes, it is.
And I'm thinking about contrasting that with the way that you talked about previously, like training the model and having that latently represented in the feed-forward network. Can you ever get, like, if you use context as a way of getting knowledge into the system, will that knowledge be represented to the same degree in the output as if you had originally trained the model with that? Like, for instance, if you're using an example of like a code that was either trained versus putting it in the context.
So here's the difference of training versus in context. In training, first of all, extremely expensive, right? Effortful. And then that shapes all of the model. So especially if you're training on, if you're trying to have the model work with something that is not well represented by the model at all, you may have to train. So one of the problems that we had, we were doing some work, Dr. Bell, you'll remember this, when we were trying to do the earliest models before ChatGPT. We were cool before it was cool. And we were working with a transformer model, and we were trying to do an assistant, but it didn't know about COVID. And so, it couldn't answer any questions about, well, what are the health restrictions? Because the models didn't know about it, and there was no way to represent it, because who on earth had ever heard of such a thing? Wearing masks? What, are we all vigilantes? No, this made no sense whatsoever. So we had to wait for the model to be retrained before it knew the concept of aerosol transmission. You just didn't know about it. If you have aerosol transmission, but now you have something else and you want to be able to discuss it, now that could go in context because it has enough to represent, even though the specifics may be here. That's one. The other is that the specifics are all available here. That may not be true in the model. The model is learning about. If it gets trained enough on things, it can learn the particulars and can memorize. But here it has access to everything. So let's talk a little bit about how you can improve the models. So here we've talked about context, and everything has been coming from the model. Everything we've talked about at this point only comes from the context and from what the model has learned. But let's say that you want the model to be able to do things that it's not able to do before. Let's say that you want it to be able to use the internet, look something up. So you could do that. You could, because the model can write things, so the model could actually write a query out to Google. Absolutely. So if you ask something, some specific information, you could train the model, and so it'd say, oh, you're asking for information which I may not have, therefore I'm going to look it up in Google and then return it to you. So how does that work? It knows that it needs to do a Google search. It does the search. So the model calls out to this tool. Then the model takes the output from that and puts it back into the context. Everything has to end up back in that context. So what page did it find? Put it into the context. Now generate your answer. Turns out you can do that with all sorts of things. Turns out that the models are really bad at math. Really bad. But it's not because they don't know mathematical concepts. That's very well represented. Notice the token here. I have a typo there. So notice the token encodings right here. All words get turned into numbers. Try this on for size. And somebody help me remember this. If you have a pencil in front of you, write down so I can remember what this number is. 41.305. Okay, here's my word, 41.305. I need to represent this as a token. Okay, I see 4 a lot. The token number for 4 is 92. I see 1 a lot, so the token number for 1 is 85. And let's see, what was the other? 41.305. 30 I see all the time. So 30 is going to be represented by my token number 5,632. And what was the last one? 5 I see a lot, and that number is 6,392. So there's my token representation. All these different tokens. And it doesn't change if I rearrange the numbers. So what happened? We chose with our initial models here, and all the models that are out there right now that are really publicly available, to treat numbers as words, which means they lose all the meaning unless we happen to memorize what's going on. So yeah, the model's going to be terrible at arithmetic. Why? Because we represent it as words. Bad tokenization. All is not lost. Instead, what I can do is I can have it call a calculator. What is 13 times 12? Oh, geez, I do not know this. Call a calculator, 13 times 12, okay, and the answer is 157? 156? 156, okay, great. The answer is 156. That goes into the context. What is 12 times 13? The answer is 156. Generate an answer. I'm glad you asked what 13 times 12 is. The answer is 156. So tools, and having the models be able to use tools is one way to extend. It still requires a context, because the answer goes into the context and is fed back through. This is where document store comes in. So we mentioned, and now I've talked to a couple of people that have created what are called GPTs. This is OpenAI's attempt to claim the word GPT. They want to become like the Coke of models, right? But the trademark office said no. But they are still calling them that. And the idea is that you upload documents, and then when you ask questions about it, it can look things up in the documents. This is called RAG, Retrieval Augmented Generation. What happens? You ask a question, it realizes that you're asking a question that it might need to look up in the documents. It does a lookup into the documents for chunks of the documents. If it finds something which is relevant, it drops it into the context and then answers your question. Note how this is different than putting the entire document into the context. The model doesn't have access to everything in the documents. Instead, it's just pulling out parts, dropping into the context, and then answering the question. Still useful. More useful for when you're doing things like asking questions. Not as useful if you're trying to summarize, synthesize, and learn a new language, right? That requires a long context. So here's the next step with these models. We now have extremely long context, plus we have the tools. And so now what we're going to be figuring out is what kinds of problems can we solve with long context and with the tools. So questions about this. Oh, Damani? Right here. Right here. Oh, yeah.
from what I can gather about these systems is they really don't know how to reason. You know, they can't follow logic on their own and come up with something. That's what it seems like to me. Am I correct about that assumption?
No.
Good.
But it's easy to, again, when I keep on bringing back to the point where it is probability distribution, it may seem like, well, it's just probability distribution, but always remember, probabilities are information. And when you navigate that probability distribution, you are reasoning. And when the model is producing additional tokens, especially when you're doing chain of thought, it is reasoning. That's why the model is able to take a book about a language that it does not know and then use that to translate. So it is reasoning, but it's reasoning in a way that's different from us. We do so in a very resource-constrained way. Our attention, our working memory is like 7 ± 2, but I think it's actually a little bit lower than that. So we are always trying to re-represent in chunk, and so we can do things, so it's very effortful. This is very broad, so it's different. It is not human-like, it is different from that. All right, let me ask you this. We are able to learn on information, on words, and we turn the words into numbers, and then we're able to learn on it through self-supervised learning. So let's say I wanted to do images. I want to learn on images. Is there anything that you are aware of right now that would keep me from learning on images? Size of tokens. I got to figure out how to do the tokens. Everything has to be numbers, right? So actually, one way of turning this regular transformer into a vision transformer is to define tokens in the following way. Start in the upper left, or maybe it's upper right. Does anybody remember? Upper left? Okay, let's do upper left. We'll do a 16 by 16 patch. We'll go and take all the RGB values. That's our token. Just call it. That's our token. Sweep through. Now you have signal. Now you actually can learn about images. Again, leave out parts. That's your token. Ablate, remove parts of the image. Have it fill in what's missing. Now it begins to learn the visual language, the language of images. So this thing is, I'm holding something and I'm right here, except you've blocked out this part. Well, what's happening? Whenever I've seen this, there's been a phone here. So this is what it needs to look like, and here's what's missing. So it learns to represent that these things appear all over the place. Sometimes they get left, sometimes they get dropped, but they're all over the place. Phone. Now, what if you had a model which had access to both the language model and the vision model? Now I have a multimodal model. Now when you begin to talk about, I was holding my phone, I was dropping my phone, I was looking at my phone, now there's a correspondence between the image and the words. So now you can have a model which is a multimodal learner and knows how to work with images and with text. Audio, same thing. I hate putting words on PowerPoint, as you can probably tell. So in everything that you've been learning up to this point, has it been written? That's all been spoken. And yet you've been learning, right? So verbal communication is a perfectly fine way of learning. So how about we have a transformer model, and we have a way of, we want it to learn on language. What's one of the things we need to solve first if we want it to learn directly on spoken language? Tokenization. So long as we can come up with the tokenization scheme, we're good. Turns out the tokenization scheme for the most successful audio transformer model is kind of a weird one. It uses what's called a log-mel spectrogram. So you first make an image, of the speech, and then you treat it almost like a vision transformer a little bit, and then you learn on that. Works fine. So it actually can learn language by looking at the waveform of the language, and that works. Video. Can we learn on video? There's nothing special about that. This is signal over time. So long as we have a way to tokenize, we can learn on it. These are general purpose learners. So some of the other things that we've been working on learning with these models, gravity waves. So we have a project with gravity waves. We have EEGs. We have speech pathologies of a couple of different types. Anything else sort of comes to mind? What's that? Handwritten text as well, learning on handwritten text. All of these are possible so long as you come up with a tokenization scheme, and you can also use self-supervised learning to learn these. All right. Let me go ahead and I'm going to hop over to, I'd like for you to be able to see in one PowerPoint what this algorithm is. This is the algorithm. Here's a fully exploded out view of the decoder, plus a little bit of encoder part in there, but decoder transformer right here with things spelled out. So this is the algorithm. It fits on one page here. This is called formal pseudocode. Don't understand what it is, not a problem, but know that you can look at, this is essentially GPT-2 and GPT-3, all on one page. It's actually a fairly, once you learn the notation, kind of a straightforward algorithm. So the lesson here is, it's not the algorithm where the sophistication comes from. It's the training is what gives these models the capabilities to do these really remarkable things. So what's the lesson here? One is, you can't write rules against us and say, don't do the following, right? You can't just put in a rule here. It doesn't work like that. That's why we have to do things. If you want to steer the model, that's why you have to do them using things like alignment. It also points out that you don't have direct access to the knowledge here. This is buried deeply in the weights. The model is self-supervised. The learning that's happening is all in the weights. These matrices represent the weights. So again, not something that you can directly and easily manipulate. And that's why we're in this interesting situation that we are. And this is also why you cannot say that the model is hallucinating and is broken and needs to be fixed. Where do you want to fix it? Is line 6 miscoded? No, the model is doing what we asked it to do. The model is doing what we trained it to do, which is to always generate the probability distributions over the next tokens. That's its job, and that's what it does. So, I'd like for us to take the last 15 minutes that we have here to actually try out some of the things that we've been talking about here. So I'd like for us to try out some prompt engineering. So I'm going to ask you to get out your computers and your phones, and while you're doing that, I'm going to pause right here and take any questions about this to give you a moment to get your phones and your laptops out. What questions do you have about what we've talked about so far and about this algorithm?
Thank you. I guess if you go back to like comparing human reasoning versus computer reasoning, I think in my experience, a fundamental difference is that whenever a thought is projected into your consciousness, there's some metadata that tells you this is a memory, this is an idea, this is a fact. Even our thoughts have some sort of like tickling thing that oh, I dream about it. I had a dream about this. This is a dream. This is a memory. I came up with this, right? And so now that you've shown us like that the reasoning is sort of like through the model, is there any way that you can like have the model tell you, oh, this is quote unquote true, or this is, I'm just inferring, or I'm just like, like coming up with, I'm just like trouble, how do you call yeah.
So let me address the first part, which is interesting. So what you're stating is that humans are familiar with the source. So I have a friend, colleague, Elizabeth Loftus, psychologist, and she did some experiments early on just to see how good our memories are. Are we a good eyewitness to our own lives? And this is where social science, this is why eye reviews are important. So, simple experiment. Long questionnaire asking about your life and different events in your life. Surreptitiously, in there, were questions about, have you ever been lost? Do you remember, was there ever a time do you remember, and these are all sorts of different questions, this is buried deep in there, that when you were lost in Disney World and the Daffy Duck character found you? Yeah, memory, the lesson here is memory is unreliable, and I don't remember if it's exactly Daffy Duck, but something along those lines. And so they answer these questions. They come back a couple of weeks later and are asked a similar question, and a fair percentage of the people then begin to remember that they had been to Disney World and they had gotten lost and they were found by Daffy Duck. Daffy Duck was not a Disney character at the time, not there. And they may have never been to Disney World. But because they'd been exposed to that in a questionnaire, it became absorbed. And so actually humans have terrible source identification. We don't know if it's something that we have seen or heard or where we've heard it at all. It gets all mixed together. Sound familiar? Completely mixed together without access to where the source is. So, I'll leave that up there for right now. So we actually ourselves do not have good source identification, and we're quite malleable in the memories that we have. Things can be introduced even incidentally. One of my favorite examples of this is memory sharing. Those of you who've been with a partner for a long period of time, I don't know if you've ever experienced this, where you begin to claim one another's memories. Ever happen? You weren't the one who went on that trip. I went on that trip. You didn't think of that. That was my idea. This shifting and the sharing of experience is actually very common. Our memories are quite malleable, and we don't have good source identification. Neither do these models. However, with in-context learning, it is much better, because in this sense, because now you can say, and tell me where you found this. Now it can begin to actually find and reference the surrounding. Same thing with if you do retrieval augmented generation. If you do retrieval augmented generation, then what you can ask for is, yes, go ahead and use this tool. Tell me which chunk you pulled in. That's exactly the metadata. So there are ways around this, but if you're dealing with things that are only in that decoder stack, you're not going to find it. It's buried. All right, you all have your laptops out? Let's go and do a little bit of prompt engineering.
We do have a question online if you want to take it.
Yeah,
or we can
go right
wait.
ahead.
You said, do go ahead? Okay.
Yeah.
So this question, I think, is a good summation of what we've been talking about. This person says, how do we see better logical and mathematical abilities emerging from the newer models? It isn't obvious to me, this person, how this would be improving without changes in the network architecture. Is there a way of understanding how more training data leads to better logic?
Great question, and I'm going to answer the first part of it, and can you answer the second part of it? Okay, great. So, first part of it is we have a fundamental problem with the tokenization, right? So we know that, can I flip over to it? So we know that with tokenization, that causes a problem because we're treating words, we're treating numbers as words. So one proposed solution is to have special tokens. Special tokens, which would be numbers. It'd be like one token which says number. That's all the token says. So if you have 5.321 number, and what was the number that I had before? That was 30.16 number. And then what you do is you encode in that vector, you actually hide that number in there, and you treat it special. That's a way for the model to actually use a true representation of the numbers, but it requires retraining of the model. So you're not going to be able to do that in GPT-4 or in Claude. That's going to require a new model with training from the ground up, but a possible solution. But Miranda, you've done some reading on and you can just do it from there if you want to, if you don't want to. So do you want to mention a little bit how models can be better trained on math?
Yes, so there are some specific models. One that I really love is Lemma, which is based on llama. It's a joke. For math people. But so it was actually trained on proofs, and so you can imitate some sort of logical abilities by changing your training data to be more proof-like, to be more logical thinking. There's another paper that I really like that came out a couple years ago called REACT, which stands for reasoning and action. And so we talked a little bit about reasoning. Can these models reason? Well, there is a framework for models stating their reasoning and then taking actions based on that reasoning. So a couple interesting ways to achieve this.
So congratulations, we're at the end of the introduction. Round of applause for yourselves for having gotten to the heart of transformer models. We're going to be breaking for lunch in just a little bit, but I want to get us started on the prompt engineering. Now you know that one of the best ways to get models to do what you need them to do is to provide more context and better context. One way of thinking of that is to think of this in terms of prompt engineering. So an early paper, Jules White is a senior advisor to, he's professor of computer science, but also senior advisor to the chancellor on generative AI. And he and some amazing graduate students, and Doug Schmidt and myself have a paper on prompt catalog. And the idea here is one way to think about prompt engineering is all the different things that you could write, right? So one way is you can have a meta language creation. So if you want to, you can say, hey, I'm going to encode this in the following way. Like if you wanted to reason about graphs, you can tell it how you're going to be representing knowledge association. Or you can, if you don't know exactly how to solve a problem, but you know who would solve the problem, you could use a persona. Take on the persona of this particular kind of expert and help me with this problem. Or you can ask it to write code for your visualizations. Or you can ask it to write a recipe for you, not just about food, but about how to do things. I'm trying to deploy an application to the cloud. Give me the steps. One of the ones that's a nice, powerful one that I will mention here is flipped interaction. You may want to solve a problem, but you don't know what information you ought to give the model for its context. So what you can do is you can say, I want to do this thing, ask me questions until you have enough information to do this for me. The model knows to ask you questions, and by answering the questions, guess what? You answer the question, you're increasing your context. Same thing is with chain of thought. Anything which is increasing that what is in the context in a useful way is going to help you solve problems. So I'm going to leave this up here for just a little bit as we begin lunch. I'd ask you to go to your favorite model. This could be ChatGPT. If you're with Vanderbilt, you can go to the Vanderbilt University, you can go to vanderbilt.ai and try that. But try some prompting. Try some of these to solve problems that you have. We'll be circulating around a bit. And do we have our TAs here yet? If the TAs are here, raise your hand. They may not be here quite yet. It's a little bit early. I'll have the TAs raise their hand before, and they'll be circulating around answering questions that you might have as well. But let's pause now. You can begin some work on ChatGPT, and it looks like we have our lunch available over here. So we're going to be pausing. We're going to have about 15 minutes. Then we're going to have a presentation from an undergraduate who won our AI showcase last year. She's going to talk about a project that she made during one of our undergraduate classes. And then we're going to begin our discussion on the afternoon on how to train these models. All right. Enjoy lunch. So we're going to have a presentation from the winner of our AI showcase for spring of 2023. The AI showcase is a new event that we started just this past semester, but we'll be doing it every semester, and it'll be highlighting the work of undergraduates and graduates in AI. And the projects come from across the university. So our next AI showcase is going to be April 19th. It will be at the Data Science Institute, and you'll be getting information. I think you all are going to be on our newsletter so you can find information, but if you're a student or if you're a graduate student and you're working on projects in AI, I hope that you will consider nominating friends or nominating yourself for the AI showcase. We have a cash prize for the top winner, and it's a great opportunity, actually for the top three. And it's a great opportunity to showcase your work with other people who are interested in AI in the broader community. So the winner from last year was an undergraduate student, Liv Lockwood, who is studying human and organizational development. She's also a data science minor and a minor in scientific computing here. She was also a student in our undergraduate Introduction to Generative AI class, which is DS 3891. Okay, good. I really should know the course number that I'm one of the instructors for. But it's a course which is open to undergraduates, and we also have a graduate level class on transformers, which is also open to graduate students as well. So see me if you're interested in that as well. But Liz did, and if we could go ahead and pull up Liz on Zoom, that would be fantastic. And do I need to pull up Zoom here, or can you actually, there we go. So Liz, thank you very much for taking a few minutes to share with the folks here the project that you did, both as your final project in DS 3891, and also that you presented at the AI Showcase. Would you mind sharing about your project?
Yeah, thank you so much. Can you hear me all right?
Yes, we can hear you very well.
All right, I'm going to share my, am I able to share my screen quickly? If not, that's all right.
Actually, you should be able to. If not, then we will create the screen share for you. One moment.
Thank you. Well, just to start, thank you so much for having me here today. Super honored to be able to talk to everybody a little bit about my project. It was definitely a passion project for me and super exciting. Oh, let me see if I can share now. All right. Can you guys see that okay?
Yes, we're good.
All right, so my project was an AI-powered ASL and deaf culture educator. The special needs community and special education has always been something that I hold really close to my heart. So when I was trying to think about what type of project I could do for my AI class, I definitely knew I wanted to be able to use the power of these new technologies to try and make a difference in the world and make the world a little bit more inclusive. So basically, this is an interactive, friendly chatbot tutor, teacher type of way to learn how to communicate using sign language while also being able to teach the user a little bit about deaf culture and deaf history, which I think is super important when learning any language, but especially learning sign language. So some of my goals of this project were basically, as I said, just to demonstrate how AI can be used to create a more inclusive world and really challenge myself. I think a big part of DS 3891 was learning about how AI can help you to do so many things that you may not have thought you were able to do before. My coding knowledge isn't necessarily that of like a Google coder, but I think I was able to make something that was definitely out of my comfort zone and really challenging and impressive. So basically how I started this off was I used the GPT-4 custom GPT to be able to create this chatbot. So one of the big challenges was that GPT-4 can access the internet, but not in the way that I really needed it to. What I was trying to do was have it go into YouTube and get YouTube videos of American Sign Language signs in order to kind of create that sentence and be able to show the user how to communicate it. So what I had to do, I really used GPT-4 as kind of my teammate when making this project. I talked to it all the time. We were problem solving, figuring out new solutions to every new problem that arose. So the first really big task that we completed was creating a Python script to retrieve all the titles and links from certain YouTube channels that had public access to different videos of American Sign Language signs. So this ended up in me creating a 40,000 row CSV file, which was awesome, but a lot of the videos weren't necessarily needed. And also, this was a lot for the custom GPT to be able to handle. So again, using GPT-4, we're able to narrow that down to about 24,000. It was still a little bit too big for it to be able to run smoothly. So after discussing with my teammate GPT-4, we ended up on a new solution, which was to put my CSV file into a web-based API in order to store all of this information and have the custom GPT directly contact the web-based API in order to retrieve the links for each video. So in order to do that, I used GPT-4 again to help me create a JSON schema to give to the custom GPT in order to allow it to do this. So what this ended up looking like, for example, what's on the screen right now, how do I sign my cat is orange? The educator is not only going to just give you the signs, it's going to explain to you a little bit about the syntax of the sentence and how you're going to communicate this properly in proper ASL and not just strictly each word of the sentence in English. So now it's going to say, can you see how to do each sign? So it's going to talk to the API that stores all of the videos and then provide a few different links with different sources for each word. So here I can click on one quick just to show here's orange. So it'll show you a few different ways to say the word orange, or if there's any different sources of how to say the word orange. And then you can also ask it a little bit more about deaf culture and history. It's very well educated on that. I basically parsed through lots of different sources about the history of deaf culture and sign language and was able to put this all into the knowledge of the custom GPT to make sure that the information was accurate and not just from random Google searches. You can also ask for specific words, and one of my favorite parts is learning about inclusivity. This is a big perk of the ASL and Deaf Culture Educator. And even if there's a word that, because this database of videos was manually created, it is a little bit, it's very possible that there may be a word that isn't in it. So if it's not, you can really talk to it, be friendly with it. It tells you, oh, here we could try and look for another word. Sure, here's another word. Here's a video. And one thing I did kind of want to highlight is that one of the other functionalities of the Deaf Culture Educator and Sign Language Teacher that I can't show right now is learning how to spell names, which I just thought was kind of funny and wanted to share because this was probably the easiest task that I had while creating this project. but due to some updates in OpenAI's custom GPT settings, now it's causing a lot of issues with showing these images directly. So I wasn't able to show that, but it definitely gave me a really big reminder of when working with technologies like this, it's constantly evolving and we have to stay really on our toes and make sure that the software that's being developed can sustain every update that comes. So yeah, in conclusion, this project was super fun for me. I was really glad to be able to show how to be inclusive and also utilizing these new powers of AI. I think the more that people put these technologies towards education and towards making a more inclusive world can be really useful and change a lot of lives. So yeah, thank you guys so much for listening. I'm so honored to be able to present, and especially thank you to Professor Spencer Smith for allowing me to really get this project going and for all the advice along the way.
Thank you so much, Liv. So, great example of what you can do with ChatGPT. Liv, let me ask you one question, though. So do you think that, that this programming is something that you could have done without, in the time constraints, could you have done that programming without interacting with ChatGPT?
Definitely not. I can 100% say no. I actually didn't even really understand what a JSON schema was when I was creating it. And that was something else that I thought was really exciting about this, because not only was I able to have GPT just make these codes for me and help me debug things, but I was really able to learn about how to do each process. And whenever I had a question, I would ask, okay, so can you explain to me what this JSON schema is doing, or explain to me what this Python script is doing? Why is it saying this? And I was definitely able to learn a lot throughout the process as well.
Fantastic. Liv, thank you very much. One more round of applause for Liv and her work. So one of the points that Liv mentioned that I thought was good to keep in mind was this ability of the importance of prompt engineering. So I'll just leave this up here again for another moment. Prompt engineering and learning how to interact with the generative AI models is key to getting what you need out of them. So I'll share the title of the paper again. Know also that Professor Jules White has a very popular Coursera course on prompt engineering, which I think at this point has over 300,000 students that have taken it, so a little bit popular. But I would highly encourage you to go to that course. We'll send the resources for that as well. The other thing that I'll mention is I think Liv's work is a great example of augmentation. Augmenting us, what we're capable of and what we want to do using generative AI to approach those problems that otherwise would have been very difficult for us to approach alone. So we always emphasize that at the Data Science Institute, augmentation, human in the loop, in empowering us in our work. So I'd like to bring up Miranda Shirk, who's going to be kicking us off and talking about the resources that we have available to us for the work that we want to do with generative AI. Miranda. Mm-hmm.
Okay, can everyone hear me all right? Awesome. Oh, cool. Okay, so I'm your second half of the lunchtime entertainment today, and this is designed for you to be able to just to follow along if you would like. You can go to the websites that I'll be accessing. We will also be sending out an email soon with resources that you can access that we've been using throughout the day. So don't feel like you're getting behind if you're not able to always follow along. Otherwise, sit back and relax and eat your popcorn while we go through how to use models as a service. So probably the most popular model as a service is ChatGPT, and you may be familiar or maybe not, and that's totally fine. When you're asking ChatGPT a question, it is not doing that inferencing on your machine. It's not doing that on your computer. Your computer is not doing the heavy lifting there. You're sending your prompt to OpenAI's computer. OpenAI is processing that and then sending it back to you, right? And so that's why it costs a certain amount of money, because they're allowing you to use their very nice computers to process these requests. And so sometimes that's all you need. If you don't have powerful machinery, if you don't have a very, very specialized use case for training your own model or using your own in-house model, models as a service is a really great alternative to hosting and training your own AI. And so we're going to talk briefly about ways that you can use models as a service and then the different ones that you can access. Okay, so the first one and probably most well-known one is ChatGPT. And if you will head to, if you want to follow along, chat.openai.com. I know most of you already know how to use this, so I'm not going to be showing you how to use it, but rather just some interesting things about it and when you may want to choose one or the other. So we're pretty familiar with this interface here. Mostly what I want to show you is ChatGPT has a couple of tiers. The first one is free. I believe you get either 3 or 3.5 GPT. And then the next one is paid for, and that's when you can access GPT-4. GPT-4 has additional training past GPT 3.5. It's very good at writing code. And then GPT 3.5 for a long time had a longer context. I believe that has since been updated. So this is some things you can do. You can also use different plugins. Okay, it's soon going to replace plugins, so I'm not going to go over that because apparently that will not exist in a while. But plugins are basically like the tools that we talked about, where you say, all right, I want to connect my LLM to a calculator. I want it to be able to do stuff like that. That's where you would use tools. One other thing that I want to point out about GPT is something that people don't always know, is you can go on here, and there was a profile on here somewhere. Okay, it's gone now. But previously there was a part where you could put in, and I'm not going to try to find that live because that would be scary and dangerous, but you can go onto your profile, go into your settings, and then kind of give it a little more information about you so that it can tailor its information. So I could put on there, I am a senior data scientist at Vanderbilt, and I teach classes on data science, but I don't know a lot about medicine, so I need more explanation in that area, something like that. You can also say fun things, like I really love to learn things through analogies about cats. And then next time it talks to you, it's going to say, oh, okay, you want me to explain this concept. I'm going to explain it in terms of cats because that's what you like. So it's also a little more fun. And then the other thing that we have also been talking about are the custom GPTs. And so if I click this button here that says Explore GPTs, don't look at my chat history too much. You can go to Explore GPTs, and there's just a bunch of them here. And this is what a lot of people have been making. These are great for when you just have a single use case. You can upload, you can describe what you want GPT to do in a prompt. You can give it a document. And then you just want to be able to reuse that. So you're not having to type in the prompt and upload the document every time. It's reusable. You can publish them. And you can also monetize them. So maybe that could be your side hustle, is creating these for people to use. There's some fun ones, like explaining Dungeons and Dragons rules and intricacies and stuff. You can also have ones on understanding policy documents. So a lot of different uses for this. And like I said, this is using ChatGPT or OpenAI's servers. This is not something you're hosting yourself, but what you're hosting on their website for them to do. Okay, and a lot of different ones here. So that's kind of when you might use a custom GPT or something like that. Of course, that costs money, so let's look at the ones that don't cost money, or at least as much money. So what I'm going to do, you can go to huggingface.co. That's huggingface.co/models is where I am here. And this was actually, we sent out an email before, which we're going to send again, where we will request that you create a Hugging Face account so that you can follow us follow along with us on some of the other workshops that we'll be doing that are more hands-on later today. Hugging Face is a great website. It is kind of one of the places that these large language models and transformers in general got started as a way for people to share their models, share the model architecture, the model code, get feedback from others. Others can use their models. Others can share data sets. It's really great, a really great library in general. And one thing that you can do here is you can access any model hosted on Hugging Face. Some of them do have a paywall sometimes, and so you have to set up your profile to have a credit card on it maybe. But a lot of them are also open source. So if we go here, I have just a couple set up that I already wanted to show you. So you can go to the models and you can type in Roberta, or you can look at the general models here and select ones based on what type of task you want it to do. But what I want to show you here is this inference API that it allows you to do. So this is their own way of allowing you to interact with the model. Maybe not a long-term solution because it greatly depends on if this model card is up and active, but a really great way to go ahead and interact with the model quickly, maybe when deciding if you want to use it or something. And so this one is specifically a question answering model. You can say, where do I live, giving it the context that my name is Sarah and I live in London, and hit the compute, and I guess it already did it. And so it's in London. They also have, you can type in your own. So I can type in, whatever I want. And sometimes they'll have a couple different examples. What's my name? Which name is also used to describe the Amazon rainforest, and given this very long paragraph. So that's another way where you're not using your computer, you're using Hugging Face's computer. And then another interesting one that I wanted to show, another Roberta model for inferencing Twitter, doing a sentiment analysis of Twitter. And so you can put in something here, and it'll tell you if it's negative, neutral, or positive. These are just a couple of the models that are on Hugging Face, depending on what you'd like to use. And then what I also want to show you is Hugging Chat. So you can get there, I believe, if you're on the Hugging Face website, click on this, and then click Hugging Chat. This is their response to ChatGPT and OpenAI. Hugging Chat is based on Meta's Llama 2 model, an open source model. And it's very, very good. It's an open source version of ChatGPT, if you would. And so great to use. You can ask it, you can turn on it. It has the ability to search the web if you want it to search the web for its answers. I haven't played around with this as much, but it has been doing pretty well. And so that's another thing. And this, I believe, is free. Don't quote me on that if they start to charge you, but always check that. Always double check that. But so just another open source alternative to using something like ChatGPT. And then finally, for this lunchtime session on models as a service, I wanted to show maybe you don't want a GUI. Maybe you want to access models through code. Maybe you want to set up your own website. On the back end is accessing GPT or Whisper or Roberta, something like that. And in that case, you don't want to use someone else's GUI, but maybe you still want to use their compute. You don't still want to use your own computer. You want to basically ask ChatGPT through like a Python code or something. And so using these API endpoints are a way to do that. Of course, OpenAI has a lot of documentation on how to access their OpenAI models. One thing that I want to show you is on Hugging Face. While we're here, any model that you go to, if you scroll down a bit, this is called their model card. It's information about the model, how you can access it. They also have the exact code that you need to get started with accessing this model from an API. And so it says, here's an example of using this model. And then it says, here's a full classification model example. What do you put in? What do you need? And then they'll have some extra stuff at the bottom here. So you can always use these code snippets to, if you're curious about accessing a specific model on Hugging Face, doing that. They also have a great library called Transformers, I believe it's just called in Python, and you can access any of the models on the Hugging Face space, as they call it, through that API there. Another great tool is LangChain as well, if you're familiar with it. We'll be working with LangChain later today, so I didn't want to go into it too much here. Okay, and that is the first part of this where we're talking about models as a service. I'm going to break for a couple seconds to get set up, and then I'm going to come back and talk to you about actually inferencing models on your own computer instead of using someone else's computer. So please let me know if you have any questions about models as a service, and then I'll see you in a couple minutes.
Hope you've had an opportunity to just chat with one another, to make some connections, and to share some of your experiences. We're going to be talking this afternoon about the training of these models. And I want to set the stage by talking about when you might want to train, the alternatives to training, and the options and choices that you have when you decide that you do indeed want to train a model. So, set the stage again. Remember, when we're training a model, what we're doing is, in that decoder stack, we're actually changing the weights there, the parameters. We're doing back propagation, and we're actually changing the model. And remember, it is expensive to do this. Remember how many parameters we have even in a small model. 7 billion parameters in very capable small models. Larger models, 175 billion, probably 500 billion parameters in the largest of these models. For the large models like GPT-4, Claude 3, we don't know how big they are because they're closed source, but we know that it is probably on the order of hundreds, all told, hundreds of billions of parameters. So training, when you're training the entire model, is expensive because what's happening is you train the model, it makes an error, and you have to go back and adjust all 100 billion parameters. Hugely computationally expensive, and expensive in dollars and in energy. So before you jump in to start training a model, a couple of things to consider. First of all, do you need to train? So we've talked about building tools here. So one way of getting a model to perform better is to not necessarily train, but instead to actually use tools. And remember, the idea here is the tools do things for you and then put information back into the context. So the model can actually have new capabilities that it didn't have before without retraining the model. See up here where it says code interpreter. What's happening here is the model writes code, and in this case it's Python code, sends it to the code interpreter runs it, gets a result, feeds that back into the context, and then it answers the question that it wrote the code for. So think about the new capability that this model has. Now it has the ability to do math, because it can write a program to do the math. It can do things that involve heavy-duty manipulation of bringing up data, joining data, lots of things that it could never do out of the box. This involves no training. This simply involves the model writing a code, sending it out, and getting the result. So when do you need to train? So one is when the model needs to learn a new domain. So information and an entire domain that the model does not have. So for example, let's say that instead of code interpreter, you had a model that was actually working with protein and protein binding. If the model does not know about any of the principles of protein binding, doesn't know anything about the field, it's not going to be able to use a tool to do protein binding because it doesn't even know how to conceptualize those questions. So when the model needs to learn a new domain, that's a time to do training. There's no other way to have the model take on a task if it doesn't even know anything about the task. There is no there to improve upon. So domain learning, and sometimes I call that domain adaptation. Another possibility is for a new behavior, a new task. So for example, there are some models which don't know how to summarize. They may know other tasks, but they don't know how to take a long text and summarize it correctly, briefly. And in that case, that's a brand new task that the model needs to be trained on. Now, we actually know how to do this, of course, because you could train the model, give it a long text, and then show it what the short version was. Great opportunity for training when you have to learn a brand new task that's not related to a previous task. Another reason why you might want to train is to have different types of behavior. We talked about alignment before. So instruction fine-tuning and alignment, also another time when you want to really shape the behavior of the model, that might be a time when you would want to train the model. But the picture's gotten more complicated, even just in the last few days. With the advent of long context models, we now have alternatives to simply training the model. So what are some of the alternatives to keep in mind even after you've decided that with the tasks that you have, you think you might need to train the model? So one is long context and in-context learning. So we talked about Gemini 1.5 and its 1 million token length context. And we heard the story of the model being given a book on a low resource language and then developing the ability to translate and to work in that language. So before the 1 million context model, 1 million context length model, that absolutely would have been a case where you want to train the model. But now you have an alternative. But consider, if you want to be able to run this model as a translation service, and you want to run it hundreds of times a day, you might have had immense savings of just doing it in context, but remember what happens when it gets to the end of the context or you want to begin a new chat. So I start a new chat, everything's gone. I no longer have the knowledge of that language stored anywhere. It only exists in activations that have to do with that context. So even though you might have been able to have the model take on the behavior in a very short period of time, maybe you do want to train the model so it has that persistently stored in the decoder stack. Because then it's memorialized there, and it can call on that information at any time. So it's a trade-off. It's kind of interesting. So some of the choice of whether or not to train the model may have to do with, are you putting it into production or not? And the cost-benefit trade-off. How much will it cost to train versus how much does it cost to do it in learning? I can tell you, just taking a look at the example of training the model on the language, you're probably talking about tens of thousands or hundreds of thousands of dollars to train the model well on that new language, easily. Whereas if you're doing it in context, you're talking about $1, maybe $10 to actually inference that. So we're talking about not just one order of magnitude, we're talking about several orders of magnitude difference between the compute and the cost of doing in context versus training the model. Keep in mind we also do have RAG, and so we have the tools. So if the model knows enough, and that combined with in-context learning may do the trick. So now we have long context learning, plus we have the tool use. So that's another option, the hybrid of the two. And then it's a choice for you to make about whether you want to have this persistent and do the proper training of the model, or whether in-context will serve. So any questions before I move on to the options when you do go ahead and do the backpropagation of the training? Any questions about in-context, tool use, and the hybrid of the two? So let's say you want to train your model. There's 7 billion parameters if this were Gemma. 7 billion parameters. And we've talked about the cost of when you're doing training of having to change all of those 7 billion parameters. So it turns out that you can have a couple of choices here, and I'm going to talk through them. One is exactly the full body training, the full model. So you're changing all 7 billion parameters. It's expensive, but you can absolutely do that. But there are other ways that you can do that as well. Maybe you don't need to have all the performance of that 7 billion parameter model. Maybe the 2 billion parameter model is good enough for your purpose. So in that case, you could instead train the 2 billion parameter model. So choosing what size of model you want to train is the first way that you can actually have a great savings on the amount of cost of the training of the models. But then there's another choice that you can make as well. Do we really need to train all of the parameters? So if we could get benefit and only train some of the parameters, then maybe we could get good performance without having to train all 7 billion parameters. Well, it turns out there is a way to do that. A technique that's been around since about 2021 is called LoRA. It's called low rank adaptation. And the idea here is that you actually segregate out some of the parameters, but they're very influential, and all you do is you train those. And it turns out that the model can take on significant new capabilities just by training a few of the parameters. Now, why is this? The reason this works is you have the 7 billion other parameters. And what these small cohort of parameters are doing is saying, okay, I only want this slice. I want to learn in this slice right here. So this is called a manifold, a submanifold. So what's happening is that these few parameters are guiding the entire model. How many fewer parameters? You're talking about less than 1% of the total. Sometimes 0.1% of the total parameters. That's a huge savings. So much so that with some of these models, and I think you're going to be seeing some of this a little bit later on this afternoon, you can actually train a full 7 billion parameter model in Colab Pro. So no longer needing to have an entire GPU farm, now you could do it on a free or a low-cost instance to train these models. Why? Because of parameter-efficient fine-tuning, and we're going to be learning more about those in just a moment. I'm going to mention one final type of training, just because it's extremely cool, it's going to be extremely influential, but it's new enough that we're not going to be talking about it. Nobody's talking about proxy training, right? Yeah. Okay. So I'm going to describe this, and then we're going to jump into the details with the data science team, the details on actually how to do this training. But I want to mention one more option for training first. I mentioned before that you have the 7 billion parameter model. The 7 billion parameter model might know a great deal. And it can do the inferencing, come up with the answer. Remember, when it comes up to this part, it's giving you a probability distribution over the next token, right? But we could also separately be running a smaller model of the same kind, but with fewer parameters. So this is like Gemma 7 billion versus Gemma 2 billion. Now, I said that you could train the smaller model to do the things you wanted it to do, but maybe you also wanted to have the knowledge of the large model. How can you do both? Paper from about 4 weeks ago called Tuning by Proxy, and this is the way that it works. Kind of mind-blowing. You train the smaller model. Much cheaper to train, just 2 billion parameters instead of 7. You train it to do the things you want to do, like you want it to train, and so it can be much more concise and precise in its responses, and maybe a little bit snarky. Maybe that's what you want. Short, to the point, maybe snarky. So you train the smaller model to be able to do that. The larger model you have not trained. But what you do is you run both models on the same input. Now, the big model has the probability distribution over the next token. The small model has its own probability distribution. Now, I've said distributions are information. So what you do is, and this is crazy, you modify, you add the probabilities over here, from here. And what happens is this model is steered by the small model. It uses its knowledge, and so it has a more informed response, but it becomes more concise and snarkier in its responses because the smaller model has been trained and is steering the larger model. It's called tuning by proxy. The purpose of my mentioning that to you is that this is a very fast-moving field. So the things we're going to be talking about today are absolutely useful. This may be absolutely the approach that you take, but know that there are always developments and may very well be developments that may speak directly to your use cases. So I would offer to you the Data Science Institute as a resource for you. So we have OpenAI Fridays, 10 to 12, you can drop by, you can talk about what's new or about the problems that you're taking on that have to do with generative AI. We take it as part of our job, keeping track of exactly what's happening in the field and keeping track of the large trends. And we're always happy to consult and to provide up-to-date information on what's next. But for now, let's go ahead and take a look at the tried and true methods and how you actually carry out this training using the tools that we have available at our disposal. And remind me, who's going to be speaking first? Dr. Bell? Is there? Yes. So Dr. Charo Bell is, would we call it a quadruple door? I think we would call it a quadruple door because you got your undergraduate, 2 of your 3 masters here, and then your PhD here. That's right. And actually, I happen to know that one of your people on your committee is in this room. So, and I believe that you're going to be talking about giving us an overview of what the training loop looks like.
Absolutely.
Now, you might.
All right, I'm going to look and see who else taught me in this room. I saw a few earlier. All right. Maybe I've already gone. But as Jesse said, I am Charo Bell. I'm a senior data scientist at the DSI, and I'm also the director of the undergraduate data science minor. I am going to talk to you a little bit more about what we're going to do in the rest of this afternoon in terms of model training. And so essentially, you can see here what we're going to be doing. Essentially, we'll start with an overview of what the hyperparameters, or actually the hyperparameters look like, why we choose or why we might go about selecting different hardware platforms, software platforms, how do we decide how and when to label those types of things that influence the model training outcomes, but themselves are not model training. Then Umang will talk to us a little bit more about data preparation. When you go to train a model, sometimes they want things in particular formats. And so if you are ready and you have your data, he's the one to talk to, and he'll tell you about how to structure it. Then we will actually go into the model creation. So our data scientists have prepared a number of notebooks for you to be able to run potentially on Colab and on the DGX A100s. And so you'll be able to try that out. And then we will talk about what it means to actually revise a training loop and think about how to make our models better whenever they're just kind of going off the rails and we want them to be a little bit better. All right, any questions about that? Anything you want me to address before we jump all the way in? All right, lovely. Okay, so a few moments ago, Jesse told us a little bit more about the different options that we have in terms of when we decide to train models. So for this part of the conversation, for the rest of the afternoon, we're going to go ahead and assume you have chosen to do model training, and now you're trying to decide what to do after that. So here you can see some different trade-offs of why one might choose to do a certain kind of hardware for training versus another kind. So on this side, these are things that are more available to Vanderbilt University or through the compute grants offered through the DSI. On this side, these are things that you would have to pay some external service for, and like this is not really an access that is like continuous. This is like a more binary thing. So just saying that for my committee member, so he doesn't judge me and take away my PhD. Okay. So again, this is things that we would be able to use directly at Vanderbilt or with a compute grant, and these things over here are things we'd have to pay for. On this bottom side, these are things that we might think of as lower computational power, even though that statement is just hilarious, given how much computational power is there at the bottom. Additionally, at this side up here, this is where the power occurs. So these will be your cloud-based computing services, your shared memory of your DGXs, and those types of things. And so before we go extra further, if you see something that looks like this, so it has those little dashes around it, that basically means that it's a way or a hardware approach that you can use where your data will be like considered to be private. So you don't have to worry about it like going out and, you know, talking to a model and it telling you something about, I don't know, your social security number. These are things that you'll be able to use. Okay, so thinking more about the hardware that we have available. Generally, we might think that maybe our NVIDIA and Windows machines, I'm sure people here have them, where you have a real GPU, which is probably an NVIDIA GPU. It's tired of me presenting already. All right, we're back. So these GPUs, they are something that you can use to train locally, as well as different kinds of Apple silicon. So those are going to be your Apple M1s and M2s. The thing about those and why they're weirdly in two different places is because it really depends on the size of the memory that you've chosen. You can have a really great M1 compute all day, but if you only have like 8 gigs of memory, you'll never train like a 70 billion parameter model. Also at Vanderbilt, we have available the Acre GPUs. So these are really great if you have a smaller sort of model or you are very interested in a specific kind of task of the model. So earlier, Jesse was talking to you about the architecture of transformers. The models that we're looking at with generative AI tend to be the decoder-only models, but there are other kinds of models that are a little bit smaller that you can also train for a particular task. And because of their size and usually the data that goes along with training those models, often Acre can be their Pascal GPUs and their Turing GPUs in particular could be really good options for that. Again, we also, have this Apple silicon. We have a lot of space that we can get. They get more expensive, of course, as the memory that's available gets larger. But they do offer a lot of compute. I will say one caveat that we've sort of discovered about the Apple silicon is that right now the compute infrastructure really isn't there as much for that hardware. Right now, if you go onto Docker, which we'll talk about in a second, but if you go and use a lot of the common packages for training models, like they'll run on the DGXs, they will run on the Turings, but they're not going to run on your M1 Max. But I'm sure that will change shortly. All right, also at Vanderbilt, we have DGXs. We have the individual ones, but also the ones that have shared memory. I think Umang will tell you more about that later. He's our king of the DGXs. In terms of commercial compute, this is where it gets a little bit more interesting. So one, you can see some things about the privacy of your data. So if you're very concerned about the privacy of your data, if you have IRB, if you have data security contracts, then you might want to go towards these ones. So what are those? So Azure AI Studio is not a model training service. It's just up here because of the amount of compute that's available. But we can see that this OpenAI fine-tuning API is also up there. So what is that? So OpenAI, they have this API where they allow you to fine-tune their models using their compute. And so you just pay for the amount of time that it trains. The fine-tuning API is relatively straightforward. And so it presents maybe a good opportunity if you want to use GPT 3.5 or the turbos, but maybe you don't want to do all of the writing of the code and the fighting of the Docker, all of those things. Also, Hugging Face. So I think Miranda pointed out earlier that that's a free service. It is a free service, except for their Hugging Face training as a service. They will take your data and whatever parameters that you need, and they will just go ahead and train your model. And that'll just be the end of it. They are happy to do that. So that is also available. OpenAI's fine-tuning API is like somehow cheaper than one would expect. They, though, are not fine-tuning GPT-4 right now, so that's, I mean, a disappointment to us all. But when we get there, I think that also will be a great opportunity. Lastly, you're going to see some examples of training here today using Google Colab Pro. Right here in the center, it has a lot of compute. It has lots of different kinds of compute, lots of different kinds of hardware. So for example, over here, we have our DGX A100s. They also have those available through Colab Pro, and TPUs and V. I mean, they have all sorts of things. Also, Google Colab, if you don't particularly have a lot of research funds or just personal funds, they do offer a free tier, but it's just that, you know, there are some constraints there about the kind of GPUs or compute that you can use, and things like that. So generally, if you are looking to train a model, we see that there are some common sort of concerns. So if you are very concerned about the privacy of your data, then the VU hardware is looking mighty good. Also, those two training services up here are also good, or I guess the fine-tuning API. But those two up there will depend on, of course, the research funds that you have available. Also, if you have tons and tons and tons and tons and tons of data, again, the VU hardware is, again, looking really good, particularly those DGX A100s. If you have tons and tons and tons of data, usually that suggests that you may be training something from scratch. A100s are perfect for that. So do think of that if you're trying to create foundation models. Something else to consider is the implementation complexity. So you just heard me talk about the challenges with the M1 and M2s. If you don't want to encounter those kinds of challenges, if you just kind of want a smooth pathway, I would say maybe the commercial compute might be a little bit easier, but there are so many people at Vanderbilt that are willing to help for Vanderbilt students and staff. I think maybe it would be a great opportunity to actually use the Vanderbilt compute as well. So also, in terms of implementation complexity, most of the platforms that we talk about are 100% into democratizing data science and AI, meaning that they're going to be making exceptional documentation so that when you go and you read it, you know what it's saying. So those are things to think about, but I will always suggest, and I love Acre and the A100s, and I'm excited for Umang to talk to us more about that. All right, so let us now assume, and I will just give you a brief overview of this process because Miranda and Umang will go more in depth about this later, but I just want to give you an overview of what it looks like to train models. And I think that you may have discussed this a little bit, but we're gonna talk about it one more time. So you can think about training models as a set of steps, right? So first you're gonna decide like what you're gonna do. Like how am I gonna label this data? Where am I gonna train my model? Where is my data? How can I move it? How can I keep it secure? All of those things, the meta hyperparameters. We need to determine all of that. Then let's say that we have all of our data ready, we have our code together, we're ready to train. Then we go into something that's called the training loop, where we train our model, and then we look to see how it's doing, and then maybe we make some changes, and then we train some more, and then we make some changes. And so I think the easiest way to think about this is thinking about yourself. So I know that we don't like to think about AI in terms of people, but I think this one fits pretty well. So in general, you may recall, studying for exams. Does anyone have a particularly good strategy that they used to use for studying for exams? Thoughts? Yes?
Just to work every assigned problem over and over again until you get it, and do every example in the textbook over and over again until you get it. It works every time.
I love that. You're going to like some of my next slides. So repetition, absolutely. Doing things over and over and over until it is hammered in your brain about what to do. Does someone else have a hand up over there? Oh, no, okay. Other thoughts? I am 100% with Dr. Peters on this one. My favorite technique was also like repetition, repetition, repetition. I had this professor during my PhD who would, of course, teach in class. It was really great. But then before exams, he would give us like this heap of previous exams. And there would be like 7 or 8 of them, and they were like super long. And generally, like whenever I got those, I would just start going through them, just doing every single problem, doing them over and over and over until I was sure about what I was doing. So it's an interesting thing to talk about. The notion of when we as people are trying to study things, we like repetition. The same thing is true for models. Whenever they're seeing data, lots of data, models will train better in the area that you want it to train if you provide more training in the area of interest. So let's say that I'm taking that test and maybe I studied about, I don't know, the ABCs, when I was really supposed to be studying about mathematics. So that would be when I provided myself a training set that was not very good. My training set should have been more composed of mathematical things and not my ABCs. So the thing is, we do like repetition. We like lots of examples that are covering the expanse of what you think that your model is going to have to answer for or have to see. But we really love that dense repetition. If there's an area that you really want your model to know extremely well, then you may provide it more examples in that area, so it'll be more familiar with the nuances of that particular area that you want it to know more about. I'm also going to go back a slide right quick. Okay. So when we think about actually studying for the exam, okay, so we're doing our repetition for sure. But what we're doing is we are looking at a question, we are generating some sort of answer, we are comparing that to the correct answer, and then we are updating our understanding based on the error between that, right? That's what we're doing. That's what we do whenever we're taking exams, not taking exams, but studying for exams when we have the answers available. This is also what your model is doing. So what it's doing is it's going to take the questions, if you will, that it's being prepared for, so the study questions. It's going to take those and give an answer, if you will, which is called forward propagation. That's also called inference. That's where we put the data into the model, and it gives some sort of answer. So it gives some sort of answer, just like we do. If the answer is super, super close to the actual correct answer, then we don't really need to make updates to what our brain representation of that question is about because we're right on. But if the difference is very large, that means we need to adjust ourselves and our minds to fix whatever was incorrect about that understanding, and we make that adjustment somehow biologically. The models do something similar through a loss function, and with that loss function, they do back propagation to update their weights in here to better represent the actual data. So it's like studying, right? You're just fixing your mind model weights to match the outputs. And just like us, sometimes we do things in batches, so I might take an entire study exam instead of just grading each one by one. The batches will help me have a higher understanding of the entire content, whereas if I just did and graded each exam question one by one, I might be a little bumpy in my understanding of my understanding. So another interesting question arises in model training, or even when we're taking exams, which is what happens when you actually get to the exam, right? So if you only studied the questions on the practice exams and you never thought about anything else, like you learned those to the T, 100,000%, nailed them, except you also never thought about anything outside of that, that would be an instance where our model would not be performing well, so it wouldn't be able to generalize. So at that point, during our training time, we are studying and studying and studying, and the difference between what we are producing and those examples that we're giving is just decreasing. You know, it's amazing. We're training really well. But then when we get to the exam, you know, we're looking at our validation from our exam. At first, we might be doing pretty well, but then As the questions are different from what we see on the actual exam or on the study exam, then we start doing like kind of poorly. So our loss starts increasing. So this right here is actually, I mean, this is what overfitting looks like. Whenever you're training your model, you will usually get curves that look like this-ish. So you do want to keep your model in this specific area. Often when you're training models using these particular approaches, what happens is you can keep training the model like way out if you want to, but what will happen is you always want to keep a copy of the model when it was doing well back here. So you can actually train as much as you want, burn up compute, do whatever you want, but just make sure that this model is saved. And that will also allow you to get a really robust look at how the model is training. So another question is, what if I had gotten in that class for the exam and it was exactly the same as another exam, like 100% on spot, or potentially it was the same as a number of exams? So what that would represent in our training methodology is if the training set is also used for testing. So if I study the exact test and I take the exact test, you would think I would get 100, hopefully. And so that means that when we're looking, if we're trying to use a training set to evaluate our model, like in finality, it means that you're going to be way too optimistic about the performance of your model. You always need to have a separate real test set that will help to understand how your model is going to generalize or how it's going to perform on data that it hasn't seen again. And professors in here, you know what I'm talking about because you definitely do that on your exams as well. If the exam is nothing close to what I've studied, that is another situation that we run into with our models. So we might train on some homework questions that were given to us by our professor. Maybe one day he gets super mad and he's like, actually, I'm going to make this test to be completely different than the study questions, and we all fail. So this is exactly what happens with models. If your test set that you're trying to predict on is significantly different from the training set, then it will usually not be able to generalize very well, meaning that you need to go back and look at the data to make sure that the data is representing what you actually want. So the last point is that maybe we studied for the exam and maybe like we tried our best, but it just didn't go very well. So maybe what we do is we go and seek out, people who have expertise in this that can give us some different study strategies in order for us to change our approach or change different parameters of our approach so that we can do better the next time. We do the same thing with models when we see that they're not performing in the way that we would want them to perform. What we do is we pivot. So we take the hyperparameters of their training, so things like learning rate, that kind of reflects how fast they're able to learn. The batch size, that's like how much data they look at a time. We take those parameters and change them to hopefully get to better performance. And usually we initially set these types of hyperparameters based on previous research. So if we are moving forward with the fine-tuning of Gemma, and Gemma has already been fine-tuned before by the creators, we would just start by using their learning rates because they're the ones who trained it. But then after that, if we find that for whatever reason our model just is not doing well, then that's when we would use our expertise as people who look at model training to understand what we should do with those hyperparameters to potentially make them perform a little bit better. All right, so that is a little overview of the model training process. We've basically said that we choose some meta hyperparameters. So those are things like how we choose to label our data, what kind of hardware that we're going to use, also what kind of software that we're going to use. And then also we said that we will expect to train our model. We need to think about the data. We know what to do if our hyperparameters are maybe not the best. And so now Uma will take us through what it looks like on the A100s.
All right, can everybody hear me all right? Great, awesome. So here is some information about our DGX A100s. We have 4 of them in 2 configurations. We have 2 that have 8 NVIDIA GPUs with 40 gigabyte memory each, so up to 320 gigabytes total on those 2 each. And then we have another set of A100s which have 80 gigabytes RAM each, so a total of 640. These are also all yoked together, so you could theoretically use all 4 together for up to about 1,920 gigabytes of GPU memory, which is a lot. So you could probably train a transformer model from scratch with that kind of architecture. We haven't actually had anyone do that. We've had someone do that with one of our smaller ones just on a single node. But it is theoretically possible. And if you are interested in doing something like that, we'd definitely be very excited to help you kind of get to that stage. These are really, really great machines for inferencing on large language models, as well as fine-tuning large language models. And the really good part is that NVIDIA's made it really, really simple and straightforward to do this. They've collaborated with Google and Meta and everybody else who's been making large language models and have created libraries and packages and Docker containers that are just designed to work really, really simply on these machines. I have personally trained a large language model, Gemma 7 billion parameters on this in about 20 minutes. So a parameter efficient fine tuning of Gemini in about 20 minutes, which is really, really powerful. If you were doing this on something that's slightly more locally available, like a Colab Pro instance, it would probably take you something like 9 hours. So it's very, very powerful to do this across 8 GPUs. One thing that I would say as a caveat, if you are using some sort of protected data, you might want to not use these. So these aren't entirely configured to handle protected data, especially like HIPAA protected data. We do not offer any guarantees that your data will be entirely safe on here. But if you are dealing with up to level 2 security data, you could totally use these without any issues because they are kind of in-network. They're local machines, so you won't really have much problem with that. In addition to that, we also offer mini grants, compute mini grants to the DSI. So this would include our A100s. It would also include any our infrastructure that we have from Acre, as well as Colab Pro subscriptions. So if you are at Vanderbilt and you need some compute access, you can definitely reach out to us and apply for a mini compute grant. So those are super, super helpful. Before we jump into actually looking at how to train these models and how to get your data ready for training these models, are there any questions about our compute options? Cool. All right. So you would have recently received an email with a link to our AI Training Day repository on GitHub. This contains all the notebooks and markdown files that we'll be kind of going through in the next couple of hours. So you can pull this up to follow along. And some of these Python notebooks are also Colab notebooks. So if you have a Colab subscription, you can also pull these up and kind of train with us. But to start, we're going to look at the custom datasets Python file. And yeah, I can make it larger. And you can hit this Open in Colab button, and you'll be able to see something like this. And I'll make this slightly larger as well. So this is a notebook that will kind of walk us through how we can create custom data sets for fine-tuning large language models. So imagine you have a lot of text, just raw text lying around, and you want to be able to do something with it. You want to fine-tune a large language model for that. This is probably the most crucial step when it comes to fine-tuning a large language model. It is also sometimes the most difficult step because it takes a lot of strategizing to figure out what you need your data set to look like. And you also need to ensure that your data set is in the right format for the specific model that you're trying to fine-tune. So if you were working with Llama, this would look slightly different than if you're working with Gemma versus anything else. So all the models have their own little quirks that you're going to have to adapt your code base for. Today, we'll specifically look at preparing your data set to work for fine-tuning Gemma, which is Gemini's little smaller counterpart. It's a 7 or 2 billion parameter model that is available open source. So the first thing that you're going to want to do is set up your environment. So that usually looks like doing a bunch of pip installs if you're familiar with Python, which basically means you're going to install a bunch of packages that will allow you to run your code. I've already done this here so that we don't waste some time, but this can take up to a couple of minutes. But all of this should run if you have access to some GPU runtime. So you can click here and say change runtime type. And if you are in the regular Colab version, you might just see CPU and maybe one GPU option. I have Colab Pro here, so I'm able to choose between T4, A100. Right now, I'm just going to stick with the T4. So the first thing that we want to do is download the model weights. So the pre-trained model from Google, you can download that from Hugging Face. What I'm doing here is downloading a quantized version of this model, which basically means it converts the weights and activations of the existing large language model from high precision to low precision. Here, I'm specifically grabbing a 4-bit version of Gemma. And so you basically want to do this just so that you're able to fit your models on a smaller machine. Right now, I'm just using a T4. This has about, I think, 40 gigabytes of RAM. So it's not a very, very powerful GPU, but it's definitely enough to get you there. But in practice, you won't be able to load the entire full 7 billion parameter model on here. The next thing that you're gonna want to do is yeah, I think so. All right, I think that's better. All right, so the next thing you're going to want to do is log into Hugging Face. So Gemma is available to us through Hugging Face, and the first thing you're going to want to do is create an access token. You can find this on Hugging Face by clicking on your profile and going to settings. You'll reach here, you can go to access tokens, and here I've created an access token already. I'm going to copy that and just paste it in here. When you run this code chunk, it'll give you the option to paste in your token, and you'll basically have logged into Hugging Face, and now you have access to all the models. Here, I'm specifically saying that my model ID is Google's Gemma 7 billion parameter. IT means it's already been instruction fine-tuned, so that means it knows how to follow some sort of instructions, but with that comes a caveat that we'll see in a second. But loading it is pretty simple, and I'll skip this a little bit because Miranda's going to go into this into more detail. But you basically load the model, give it the quantization configuration, tell it what GPU you want it to load on, and then it downloads the model for you. This takes a little bit because even a quantized version of this model is something like 15 gigabytes, so it'll take a second. So we're going to work with a tutorial data set, and then I'll also give an example of a real-world data set that we created. So a good example for this is the data set provided by Token Bender on Hugging Face. It's called Code Instructions 122K Alpaca Style. Alpaca Style just means that it's been transformed into a style that works well for instruction fine-tuning, specifically with the Alpaca model, but it's a good starting point to use for Gemma. So I just load the data set, and I just grab the training set because that's what I'm interested in. I'm going to convert it into a pandas data frame so we can actually see what this looks like. So as you can see, there's input, there's an input column, there's an output column, there's an instruction column, and there's a text column. So essentially, the text column is basically all the columns combined together, but the instruction column contains the query. The input columns contains the inputs that would be necessary to sort of complete the query, and the output contains the desired response. So all of these are sort of questions, or programming questions. So here it says create a function to calculate the sum of a set of numbers. The input is 1, 2, 3, 4, 5, and the output would be some Python code that allows you to do the sum of a couple of numbers. So the biggest thing to understand here is when you're instruction fine-tuning, your data set essentially, at the bare minimum, needs to look like input-output pairs. That's what you're going to train on. You want your model to accept some type of input, which is going to be some sort of instruction, and you want it to generate an output. And you're going to want a pretty hefty number of these. Here we have 122,000, so you're going to want your data set to still be pretty large. And that's also where some problems come in when you're working with your own data. So here's an example of how we converted sets of unstructured data in our medieval French project into a training data set that can be used for fine-tuning a large language model. So here we have text. These are poems in medieval French from the 1100s. So this is just lots of lots of raw text. And then we have their English translations, but chunked up. It's like lines 1 through 18, it's a little hard to see, but lines 1 through 18, here's the translation. Lines 19 to 38, here's the translation. So I have these two sets of raw data. I wanted to convert it into a simple data frame, which has English and French as a column. I didn't really know how to do that, so I asked ChatGPT. It created code for me, and it basically, I uploaded all my files, and it gave me a data set, and I downloaded that as a CSV file. Super simple. In practice, this might be a little bit more difficult depending on what your data looks like, especially if you're working with other modes of data like audio, video, images. It's going to be a little bit more complicated. But essentially, I ended up with this. And this is exactly what we needed. And so the next step would be to format your data set for the model that you are working with. So Gemma has a very specific format for the instruction template. So as you can see here, it's start of turn, and then user, and then that's your actual first query, and then end of turn. And then again, start of turn, model. This suggests that, OK, this is the actual output. And then there's the model output, and then end of turn. So every single data point in your training data set needs to look exactly like this. Gemma provided us a function that does this for us. So essentially, there's some prefix test, which is below is an instruction that describes the task, write a response that appropriately completes the request, and then it formats that data file that you have, which is inputs and outputs, and adds a column to your data set, which is called prompt. And that's really what you're going to be training on. So if you look at the first data entry in your data set, now it would look something like start a turn. Here's the instruction. Here's the actual input that you provided. Write a response that completes the request. Create a function to calculate the sum of a sequence. Here are the inputs, so it also put the inputs. So that's your actual input between the start of turn and end of turn. So that's what the user is going to ask. And then in a new line, start a turn, this is what your model output should be like, and then that's the actual expected answer, and then you end it with end of turn. So every single data point needs to look like this when you're training. It can be a little annoying, but they've provided us with a lot of helpful tools that can make this a pretty straightforward process if your data is not already too complicated. So now that you've successfully created a data set, you can just go ahead and fine tune. Miranda's going to go into details about what that actually looks like, but I wanted to also briefly talk about what this would look like if you were working with image models or audio models. Yes, question?
How do I get the page you're looking at here? I'm signed into CoLab, but I have no idea how to get custom data sets on Pi.
Sure. You would have received an email maybe an hour ago. And there is a there's a GitHub repository there called AI Training Day. It should be one of the first ones under must-have. All right, awesome. Other questions before I talk about other modalities? Cool. So yeah, it's relatively straightforward getting your data into the right shape, but it can be pretty complicated depending on what your tasks are. This was a simple translation task for us here, so it was fairly straightforward. We had English text, French text, just put it together, right? In practice, we didn't actually end up using this data set because about 3 days after we created this data set, Gemini came out with their 1.5 model, and we tried it out, and Gemini already knows medieval French. It actually knew this exact text. So we pivoted, and now it's a sort of prompt engineering project more so than a fine-tuning project. But let's take a look at what this looks like for images. It's a lot harder. You're going to have labeled data, and that's what really makes it pretty complicated. For example, this is object detection. You can load an image, so this is an image file. But you need to have your bounding boxes if you were doing some sort of object detection already ready. So you'd need your object IDs, and then you'd need the bounding boxes for all those object IDs. So this is a lot harder than working with text, but Hugging Face has provided you with a lot of great resources. If you were to go into just docs at Hugging Face and go to transformers, you will see all the possible options you have for image classification, segmentation, even video classification. This is brand new. I actually didn't see this yesterday. And for audio as well. You can see that here. Audio classification is also the same. You're going to want to have pre-labeled data sets, which can take a while to prepare, but once you're ready, training actually looks pretty much identical. Once you have your data sets ready, training these models are almost identical. So, Miranda, I think I'm going to hand this off to you so we can now see what the training loop actually looks like in practice. And after that, we'll see how the training loop looks like in practice on the DGX as if you were to do something a little bit more large scale where you wanted to use multiple GPUs and do that really, really quick fine tuning of a 7 billion parameter model in about 20 minutes. So, Miranda.
You found a quick overview of what it looks like to think about, first of all, how to think about training models. Umang gave us a quick overview of what it looks like when you're actually training the models. What we're going to be doing now, we're going to take a little bit of a break. Both for people who want to be able to get into the correct repo, we'll have our assistants moving around. We also want to have an opportunity to recharge. Even though we just had lunch, a little bit of caffeine would not be bad at this point. What we're going to be doing next is we're going to be slowing down a bit and taking a look at actually how to use the code to train models. So we're going to be looking at this in a number of different ways. One, we're going to see what it looks like to train a model just in Google Colab. Google Colab, a free or for low-cost compute, you can actually do training of models there. That works. We're also going to be taking a look at what it looks like to train your models locally and also to train your models on the larger systems such as the DGX A100s. We're going to be sticking just to the large language models and just the training on text. But no, just as Umang sort of mentioned here, you can train models in other modalities as well, but it does require a little bit more assistance. Pro tip, GPT-4 and Claude are great assistants at helping you figure out what you need to actually do in order to train not GPT-4, but to train large language models. So, before we break for a snack, and we have the TAs who are wandering around to help you get set up, so you're going to be ready to do some hands-on stuff after our break. What questions do we have before we take our 10-minute break here? All right, go and grab some caffeine, some popcorn, and we'll get started up in about 10 minutes.
Awesome. Okay, so I know that we had some confusions on getting to here so that you can access our files. So if you registered for this conference, step one, and you to receive the email, in that email you should have the link to our repo. But if you did not, and that's totally fine, we're happy to have you here. Please make your way to github.com/vanderbilt-data-science/AI-training-day. And then we'll all be good. So yeah, if you need to take a picture of that, go ahead and do so. And if you are having errors or code problems, wave your hands, and we have our lovely TAs that are helping us with this, and they will get that sorted out. If you have a question for me, I guess somehow we need to differentiate between that. So wave your hand frantically if you need immediate help from a TA, and just kind of calmly raise your hand, I guess, if you want to ask a question. So, all right, so in this portion, we're going to be talking about how to actually fine-tune your models so that you can train them yourself. And so Umang took us through how to make our custom data sets. And now we're going to have our custom data set. We're going to preload one as if we just made it. And then we're going to fine-tune Google's new Gemma model. That's the open source model. We're going to fine-tune that ourselves. So if you make your way to this GitHub repo that we have, and then select DSI AI training. And that's not right. All right, we've got an infinite mirror thing going on here, so let's not do that. Let's see, is that better for the Zoom? One moment. Okay, so click on DSI, AI training, yes? I understand now. Apologies. Okay, so if you click on DSI AI Training Fine-Tuning Gemma, you should see this Open in Colab button. That is for you to be able to run. So if you click on this, it will open in a new tab, or sometimes the same tab, and then you can run this yourself. It's your own copy. Don't worry about saving a copy of it, changing the code. It's not going to show up on anyone else's. It's completely yours. All right. Let me see. I'm going to zoom in a bit. So hopefully we're all able to make it to this part. Can one of the TAs help open on Colab? Thank you. Yep, click on the file and then go to Open in Colab. Okay, so hopefully we are all on parameter efficient fine-tuning Gemma. I'm trying to look around to see if I see any very panicked faces. All right, looks like we're mostly on the same page. So this was largely obtained from Gemma's own documentation that they put out, and supposedly this whole thing can be done on a free tier of Google Colab Pro. A free tier of Google Colab. And so if you don't have Pro, that should be no problem. You should be able to run it. Although I do want to caution you against running the same code multiple times. So if you go down here and you run this 5 times, you might blow through all of your compute. So I just want to say that. Make sure you're only running the code cells once. And if they work, then you're good. You don't need to run them again. A couple of things that you will need before we start, and this is also in the email that we sent out. Our TAs can also help you with this. You will need a Hugging Face account. You can get that at huggingface.co. You will need to log into your account and then visit Gemma's Hugging Face space. I have this linked for you here, but if I go ahead and click on this, it will take us to Gemma's model card. We talked about this earlier over lunch, where we have model cards that describe how you can work with a model. In Gemma's case, it is free to use, but it is gated, which means that you need to accept their terms and conditions before you're able to use it. So in my account, I have accepted the terms and conditions, and you can see that it says, you have been granted access to this model. What you need to do if you have not done this yet is you need to go to Gemma's page and then click the little box that says, I accept the terms and conditions. It gives you access instantly. So there's no waiting period for that. And then the final setup for this notebook, and again, please ask our TAs for help if you need it, is to be able to get a Hugging Face API token. So if I go to my Hugging Face account, I'm not going to show you my API token, but I'll show you how to get one. You can go to Profile, Settings, and then it's right here, and Access Tokens. All right, you only need a token with read permissions. Like I said, all of this is written down in that email. We have TAs to help you, so don't get overwhelmed. Back to the code. So I have already run this so that we're not waiting on me to log into things while I'm explaining this code to you. But the first thing that we need to do is to input our Hugging Face token. This is a way for Hugging Face to monitor who is accessing what models. The models we'll be looking at today are not, they don't cost money, they are free to access, but they do still want to see what you're doing with the model, so they require authentication. Much like with Umongs, we have a couple of pip installs to make sure that you have the correct libraries here. And one note that I want to say, which this is an error that I've run into before, and I've already seen some people hit this. If you get a weird error when you run one of these cells that says, you must have accelerate and bits and bytes installed, that error is very poorly written, and it should actually say you're not connected to a GPU. So I don't know why they say that. Instead, so if you're not connected to a GPU, click on this. It'll let you change which one you want to connect to. OK, yours shouldn't look like this. Yours should look more like this. Make sure there's a check and it says T4, not CPU or anything. TAs can also help with that. All right, now that we've got all of that out of the way, let's get into the actual interesting part. So Gemma is the newest suite of open source models released by Google. And very awesome. They are on Hugging Face, and we can access them and then fine-tune them for our goals here. So in this example notebook, I'm going to be taking you through a way to fine-tune the Gemma 7 billion parameter model and fine-tune it to be able to make quotes and then attribute them to the correct author of that quote. And you'll see what I mean here in a second. So the specific data set that thing is called the English quotes data set. We're going to load that from Hugging Face and pretend like we used Umang's code to pre-process it. It's already pre-processed. And then fine-tune. So the first thing that we're going to do is select our model. You can change this to be whatever model you want. I'm doing Google Gemma 7 billion. If you wanted something else, for instance, 2 billion, you could replace the 7 with 2. There's also 2 billion instruct, which just like Jesse was saying before, that's like the difference between the dog that looks at your hand or the dog that looks ahead, if it's going to follow instructions or just complete your sentence for you. Bits and bytes configuration is just a nice configuration that helps when you're working on GPUs. You don't have to worry about that too much to understand what we're doing, so I'm not really going to explain too much in that. But the main thing that we want to set up is our tokenizer and our model. So our tokenizer, we will give it our model ID so it knows we want to use Gemma, and then we're going to give it our Hugging Face token so we can log in. And next we're going to set up our model. So we're going to pull up the model with our model ID, send it that configuration that we set up, and then we just have some stuff here to access it. This is to access a GPU, and then this is also to set up our Hugging Face authentication. So mainly what we have done in this cell here, we've imported some stuff, we have chosen our model, and then we have set up our tokenizer, which is going to take in our data, right? Remember when we talked about tokenizers this morning? That's going to tokenize our data for us, and then this model is going to be what we are actually training. Okay, so any questions on this setup part before we actually get to the fine-tuning part? I think we have a mic somewhere.
As far as making the decisions on the tokenizer and the model and all that stuff, how much should I care?
That's a good question. For this tutorial, you shouldn't care at all for the purpose of today. But let's say you have not as many resources to be able to train. So you maybe want to choose 2 billion parameters instead of 7 billion. Let's say you want a model that follows instructions rather than completes a sentence. And in that case, you want one of the instruct models. So I think it just adds an IT or something like that to the end of the ID. As far as the tokenizer, you're typically wanting your tokenizer to match the model that you're using, because it would be inefficient to use Llama's tokenizer when you're training Gemma's model or something like that. So you typically want those to match.
Cool, thank you.
Yes. Great question. Do we have any others? All right. And scroll down. And if for some reason you weren't able to access a GPU, I do have an option here for CPU, but I have not tested it. Okay, so next thing that we want to do is we're just going to say, okay, how does our model do right out of the box? When we take our model, I say, okay, this model, I want it to complete quotes for me, and then attribute that quote to someone. So I'm just going to throw something in here. This is an example from Gemma. I'm going to say, quote, imagination is, and I'm hoping it's going to fill it in for me and then tell me who said that quote. What this is doing here is setting up our GPU again. Hopefully you have access to it. And then we're going to send it our inputs. This inputs here, notice that we're setting up our tokenizer, inputting that text, and then you don't really have to worry about this part. It's just saying, return it in a way that Python, PyTorch can understand. But what is important here is this outputs. So we're asking the model just by itself, generate something after I give you this input. So this is like if you went into ChatGPT and you put in your prompt and then you hit enter, except now we're doing it in Python. So quote, imagination is, and now I'm going to print what the output of that prompt is. And for Gemma 7 billion base model says, quote, imagination is more important than knowledge. Albert Einstein, I am a creative and curious person who loves to learn. It kind of just kept going and adding more quotes, I guess, that it knows by Albert Einstein. That's not exactly what we want it to do. Instead, we want it to just give us a quote and then tell us who it's from. So not exactly what we want. And this is before training. So this is to show you what it looks like before we actually do fine-tuning. So next, we're going to set up our training configuration. We're using LoRa, and that's supposed to be a nice link. That's OK. If you want to learn more about LoRa, you can read this guide here. It's very nice. And then we can use the parameter-efficient fine-tuning library to load the LoRa configuration. You don't have to worry too much about what we're doing here. I don't want to get into the weeds, and I want to make sure that I keep this talk interesting. But you can take this directly from Gemma. They show you exactly how to set it up. And unless you really need something specific for your use case, I don't think you'll need to really tweak this a bunch. We're loading our data set. Remember what Umang took us through. This data set comes straight from Gemma because it's one of their example ones. So it's already formatted in the way that we want. But do see Umang's tutorial if you want to know more about how to structure your specific data. So we can pretend like we already loaded that here. And it may take a while, but it's going to look something like this when it loads. And now we're actually going to start the training. So the fun part of this formatting function is basically going to take anything in our data and prepend it with quote, insert the quote there, and then author, insert author here. That's what we're telling our model that we want to format the output as. And this is just required from Hugging Face as something like, how do you want to format the inputs and the outputs for us? Set up your supervised fine-tuning trainer here. We input the model. We input our training data set. All of these you can mostly keep the same unless you really know what you're doing or what they mean. If you don't, perfectly fine. What is important here is the parameter-efficient fine-tuning config. Parameter-efficient, that is what is allowing us to tune it on our free instance of Colab or on our laptops if you're doing that. That's allowing us not to have to train every single parameter. And then pass in our formatting function. And from there, it's just trainer.train. And it seems a little too easy to be true. And if you are, at this moment, worried about some of these extra arguments or all of this extra stuff that gets thrown in there, just know that a lot of people are just copying and pasting the same parameters, especially if you're learning. So don't get too caught up in that. This is literally just taken from Gemma's website on their model card. So if I just show you here, there we go. There we go. See, they give it to us. So it's OK. And then we can sit here, and it will take a little bit, but you should be able to run through it on your free instance of Google Colab. And this is showing how many times we're running through our training loop, the number of epochs or steps, as some people like to say. And if you're not a machine learning person, all you need to know is that this is loss. That means how wrong is our model. We want that number to go down. And it is. It's going down. OK, so now our model has finished training, and it's going to say, all right, we finished training. We used 10 steps. We got our loss to go down. And now we can evaluate it. So what I did here, just to summarize, we were loading our data set. It's already been formatted for us. We have set up our model by accessing Gemma from Hugging Face. We have put in our authentication and all of that, set up our training routine, and then just said trainer.train with our new data set. That's all you need to do to set up to fine-tune these models. It's pretty amazing that you're able to do this. So now if we evaluate, how does it do now that we've fine-tuned it? We're hoping it does better on our specific task. And it does. So I put in the same prompt here, quote, imagination is, run it through our model. It says imagination is more important than knowledge. Author Albert Einstein, from the world as I see it. This is exactly what we wanted for ours. And so you can imagine doing this for your specific use case. Use the, customize your data set to fine-tune Gemma, and then come up with, you could have one where you say, I want it to help me tell data science jokes, and maybe you have an entire data set of data science jokes, and then it can tell those to you. Or maybe you have a very specific use case. You have a lot of documents that you need to go through or something very specific to your lab that it needs to be able to generate, able to use this fine-tuning method on this as well. So finally, once you have fine-tuned your model, you can use PyTorch to actually save that model. And I should have, you can hit run anyway. I'm not putting a virus on your computer, I promise. You can hit this to save it, and what it's going to do, if you're not as familiar with Colab, you can click on this folder here, and once you save the model, it will show up there as something you can download. Or if you're on your computer, you'll find a file that says this, and that will actually save your fine-tuned model so that you can use it later, load it wherever you would like.
Do we have to run all the ones under evaluation? Looks like it did everything already, but I'm not sure if I need to run the quote.
So we just have a question about Google Colab.
Yeah, under evaluation, right? Everything else ran, you know. I've got the 6 epochs and 10 steps or whatever. And now under evaluation, do I need to run that, or has it already been run?
So it depends on, can I have a TA come help? You can run all the cells. I do suggest that you do. You may already have the output because it was saved. I saved it so that people could see it even if they weren't able to run it. So it kind of depends on what's on your setup right now.
What's been executed and what hasn't. Obviously, everything before evaluation has been. Thank you.
Yeah. Awesome. Any other questions? We have plenty of time. I think I'm very under time right now. Can we get the mic?
I didn't get the same answer that you got. So
Okay.
What does that mean?
Yeah, so these are generative models. So it's outputting, you know, a probability of which one. So it may not always output the same thing. I'm just curious, what did yours say?
It just repeated, so it did the quote, author Albert Einstein, author Albert Einstein, author Albert Einstein.
Oh.
So it repeated the author like thrice.
That's very strange. I have tried this notebook several times and it never did that. So I don't know.
Cool.
Same. Interesting. Okay. Well, you know, live demo never works, but that's interesting. I would want to see it to see kind of what it's doing. Thank you for bringing that up. Other questions? All right, so hopefully we have given you some methods to fine-tune your models on Colab. I believe Umang is going to go over how you can use a very similar technique to fine-tune on DGXs for something where you may need more compute. So we will go ahead and transition that. Oh, actually, Charo is going next, I think. Sorry.
So much, Miranda. We're going to pause here and let people get caught up and try the training. I'll point out that what you just did was you trained a 7 billion parameter model to take on a brand new type of capability, which is to respond differently when presented with quote and then part of a quote. That's significant new capability that you've carried out probably on free compute. And it's possible because of parameter-efficient fine-tuning. So that's been a real revolution in the training of these models. But let's go and give ourselves about 5 minutes to go through. Be sure if you got stuck and you weren't able to actually carry this out, go ahead and wave your hand and our TAs will get to you. But go ahead and take a few minutes to make sure that you're actually working through that. And then what we'll do next is we'll take a look at going through another training loop, but this time on M1 or M2 or M3 max. I'll make a quick note of why you might even want to do that. Think about security. Think about having a very private model or wanting to train on proprietary or sensitive data. One way to actually do this is to train on hardware which is physically in your possession. So if you're concerned about secure models, this is absolutely one way to do it. So we're going to take 5 minutes. So if you're all done and ready, just grab another snack, but we'll start up again in 5 minutes.
All right, I think we're ready to get back started. Coming on back from our break where we successfully trained Gemma. Good work with that. And now we'll talk a little bit more about local models, and then we'll talk about the DGXs. So we've already talked about that some of the high-level decisions that we have to make are around hardware. Where are we going to train these models? It impacts how much data we can train with, how fast it'll take, how much it'll cost, all those great things. But there are also additional considerations, like what kind of software are we going to use? Like how are we going to support it programmatically, the execution of this code on the hardware? And so that is where some different mechanisms for doing that kind of versioning on software come into play. So we're going to take just like a quick little side quest into a little bit of just computer architecture for just a second, just so we know some of the things that we're going to talk about. So it'll be more familiar. You'll know what I'm talking about. Okay, let's talk about this stuff. I know you got, maybe some of you don't. I think you've all seen a tower, right? Hopefully. Okay, good. All right, so we've all seen the tower. This is clearly a computer. And as we know, computers have some different parts. We can think about a computer as running some applications. In fact, this computer is running lots of applications. It's running HTML right now to make this slide set. We have different kinds of operating systems. We have different kinds of memory associated with different kinds of processors. We also have different kinds of processors and different underlying architectures of those processors. Do you believe? Does that sound familiar? How much of it sounds familiar? Because I'm about to put you to the test. Okay. Test one. Name a program or app that is running on your computer right now. So maybe, it depends what kind of, okay. Other thoughts? Don't be shy. Beautiful. Every browser window known to man. I definitely have 1,000 tabs open. Okay, so we said Google Chrome, Edge, maybe Safari, other apps that are running on your computer. Zoom, perfect. Another application that runs on your computer. Beautiful. All right, tell me about what operating system you're running. Anybody know what operating system they're running? Sonoma, okay, so Mac OS X, okay. Other people? What's that? Windows, great. So if you are not quite sure, and you're on a Mac, what kind of operating system you're using, one thing that you can do is go up to the Apple. Hopefully you can see that, probably not. But you go up to About This Mac, and you click on it. And it will tell you many a thing in small font. So go click on yours, because you will find it informative in our next steps. All right, somebody tell me about the size of their memory on their computer. 64 gigs, beautiful. Other folks? $16, nice. Other folks? Do we know where to find that? If you're on a Mac, again, we go to the same Apple, And we're about this Mac. So I wish I could make that a little bit bigger, but I can't. You can see there's some memory on this computer, and there's a reason for that, and that is because it is an M2, and it has this shared memory between CPU and GPU, which is interesting for training models, because that's what I can fit on there, something 96 gigs. You can also see the operating system that I'm running, which is going to be OS X, but also this is the specific version of it that I'm running. You can see exactly what kind of chip I have, meaning that you know what kind of processor-ish that I'm using, which is this one. So that's the M2 Max. Does anyone else have an M2? M2, anybody? M1, anybody? Windows. Are most people Windows? Okay, Windows. GPU on board or no GPU on board? GPU on board, nice. GPU on board, anybody? All right, nice, okay. So I think we have seen that some people have different kinds of processors. We can think of the CPU as something that runs, it prefers to run things in order. So if you show it like a line of people, it loves to see that. If you show it like a set of parallel lines of people, it's a little bit disappointed. However, the GPU is really excited to see parallel lines of people because it likes to process them in parallel. Okay, great. So let's see the last thing that is actually a little bit weird that we cannot see, and it's like hard to find, is the actual architecture of the chip. And one way to figure that out is to do it in Python, but generally you can kind of, some computers say it, especially Windows machines, they tend to be a certain kind of architecture. Macs tend to be a certain kind of architecture. There's two kinds, and then Linux computers tend to be a certain kind of architecture, so you can kind of make some assumptions as you go along. But here are some examples. So we know that our applications, these are things that run on our computers. So we have Word, we have PowerPoint, we have Chrome, like people said. We also have some operating system. The operating system is going to orchestrate the things that are going on your computer. So whenever you have high utilization of something and it's like skipping around trying to figure out how it's going to serve you up this new application that you're opening, when you have something that's taking up all the resources, like that's your operating system trying to help you out. Also, it is what allows you to run these programs, and it runs them in a very specific way. So I'm not sure if you have tried this, but if you've ever tried to download a Windows-based program onto a Mac, it's not going to work, and vice versa. It's also not going to work, often because the problem is the operating system lack of compatibility. With the memory, we've already talked about the fact that there's different kinds of memory. So there's CPU kind of oriented memory normally, and then there's GPU oriented memory. They do similar things specific to what kind of memory that they are, providing memory essentially. And sometimes some people have shared memory. So that is what we have when you have an M1 or an M2. In terms of the processor, that is what will help you understand what exactly is your computer architecture. You can find these online, but sometimes you do can just go with what you know about that particular operating system and the chip that you're using. You can pretty much assume that if you're on Windows, you're probably going to be x86. If you are on a Mac and it's an Intel chip, then you're probably going to be AMD. If you're on Linux, you're probably going to be an AMD. And if you're on M1 or M2, you're probably going to be on ARM. So there's just some general things that we expect when we're running on different kinds of computer. Why do we care about any of those things? So the reason that we care about those things is often when we work with other people, or if we want to move our code from one place to another, we need to be able to have the same environment in one place as we have in another. So I'm not sure if this has happened to you before, but two people can be working on a project together. If they don't have the same environment, the code that one person writes doesn't run on the other person's computer, and vice versa. And then you have to figure out what the package versions are. You have to do all of this slicing and dicing to understand the minutia of one version point number. But it's better to just start with the same computing environment. The problem is that we have all different kinds of computing, right? I have a Mac. Some of my coworkers have Windows. They have different kinds of Macs. So how do we standardize a computing platform when we have all these different kinds of computers with different amount of memory, all these different types of architectures? How do we do that? That there is a good question, and there are a lot of approaches, actually some few main approaches for doing this, but we really do like to see that the computing environment is the same if we move to another platform. So let's say I start developing on my Mac, and then I go to the DGXs. I want that to be at least similar if it can't be identical, but it also can be almost identical. And if I am working with someone else, I also want them and me to be able to share the same computational kind of environment. Finally, in terms of reproducibility for the faculty members out there, for the students, it helps you to have the same package versions whenever you go from one project to another or from one person to another. So let's say that you do some research, you use a particular kind of code to do that, maybe it has a particular version. 7 years later, someone wants to run that code, and so all the package versions are 7 years later. You can give them your Docker container, they can run it in that container and have the same environment that you had when you developed it. So in terms of reproducibility, a lot of these ways that we're going to discuss are major pluses for the academic processes that we're after. So the question is, how do we do these things, okay? So again, there are really two main ways that we tend to do this. One is through virtual environments, so not virtual machines, virtual environments. Virtual environments are offered through something called Anaconda. Anaconda is a friend to people who do data science and for people who do machine learning, AI, because it essentially is going to be installed on your computer and it's going to come with a lot of the Python packages that you already wanted. So if you ever wanted to do tabular data analysis, so maybe you're at work and you have some data you need to analyze and you think, oh my gosh, today is the day that I use Pandas to do this. If you have Anaconda installed, you already have that package available to you without having to do a lot to make that happen. So we do like Anaconda. It's a friend. Sometimes it's a little bit big though. And so there's another offering called Miniconda. And again, this is something that comes installed with all of the main packages that you will need for generally Python and data science. But people like Miniconda because it is smaller. So with Anaconda and Miniconda, you get the capacity to use virtual environments. So what does that mean? Okay. So let's say that I decide to work with this half of the room on a project. We are training Gemma. We're training Gemma on this side, okay? And then I decide to work with this side of the room where we are training Llama. We're training Llama. So for whatever reason, Gemma side, the package needed for that, for parameter efficient fine tuning, whatever have you, that's version 2.0. But with Llama, it's version 3.0. So when I get on my computer and I try to start working on Gemma, that means that I have to switch all of my code over to use version 2.0. And then 10 minutes later, when I want to do something with Llama or want to check something for my teammates, now I got to switch it back to 3.0. And I don't even remember which version that I just said for either of you. So it's going to be an issue. So enter virtual environments. These help you to separate your packages for your projects into essentially different lists. So for this project on this side with Gemma, I would have a different package version that I could just switch into. It's like going into a different room over here where I have different package versions. And then when I'm ready, I can switch into this room over here where I have the package version needed for that. And that's what virtual environments are. They're just little specific lists of the kind of packages that you need for that specific project. So with virtual environments, you'll see that they're normally named after your project. So they might be, I don't know, law transformers or something, because in that project, I have a specific types of packages that I need to make that code run. On the other hand, I might have a stutter project where we're using audio models. And for that, I need yet another set of packages. So that allows me to keep them separate, switch from one to another whenever I feel like it. This is a great approach. Wonderful, lovely. We also like Anaconda and Miniconda because they are not just Python package managers, but they are like environment package managers. So for example, if you needed a specific version of Java in one project, and you needed a different version in another, that's something that Anaconda could do for you. So we do like Anaconda. There is another virtual environment like software. It's called VM. It comes through pip. We like pip. Pip is okay, but it is yet missing that piece that we like with Anaconda, which it gives us the more full environment with the other kinds of system packages like Java. Okay, so you can see here, this is an example of literally what the virtual environment on my computer looks like literally right now. So here it looks like this. It's just another folder. There goes Miniconda. Bin is where all my packages are. So essentially, if you were to go look in there, you would see like pandas or plotting or whatever packages that I need to make my code work. So I would have like the parameter efficient fine tuning that you just saw, the transformers that you just saw, the Hugging Face CLI maybe that you just saw. It would all essentially be somewhere in this folder. So now, when we go down, we can actually see the environments. Here, this is the name of my environment. You know just what it's for. Trying to train an XLLM. I like to call them XLLMs because they're like super big LLMs. So XLLMs, trying to train them on Apple Silicon, and you can see that there are some specific packages related to this. If you were to look at other environments that I have, they would have different versions associated with them as well. So again, you can see if I were to switch somehow into this folder, I would have these specific versions. And if I were to switch into a different environment folder, I would have access to those versions. And that's the way that you can think about it, except for there's no folder switching. You just do it through like an underlying sort of program that's running. That is our virtual environments. The one pitfall of virtual environments is that they're missing just one other piece. And that is well, actually two other pieces. But they're missing the notion of the kind of operating system that you're using. So with Conda, or Anaconda, with Miniconda, you can't like give the whole entire like software piece to someone else and say this is the environment in which it needs to run fully. It needs Linux, this specific version of Linux, and it needs these Python packages. You cannot do that with Anaconda, but you can do it with Docker. So this is a picture directly from Docker's website. So you can see that there's a little bit of something different going on here because this looks like a bunch of folders. So what's going on here is you can see that like the host operating system, that is your computer. So you remember how we just talked about operating systems? That's why. So if you're running Linux, if you're running Sonoma, like someone said, that is where your operating system is between this thing called the Docker engine, which is the thing that is like running the containers and like making them work. And then that is between the infrastructure. And what's meant by infrastructure is like a few different things, but you can generally think about it as the hardware that you're using. So my hardware is gonna be different than your hardware, and it's gonna be different like around us. But what we will see as we are looking into this Docker container is just this. So we're just going to see our container instead of seeing the host operating system. Well, we'll see that a little bit, or the infrastructure. So what's going to happen is we are essentially going to build these containers. And whenever you think about a container, you can think about it as like a Ziploc container. You put stuff in it, and then it's separate from the environment. With a really good Ziploc container, you can like put stuff in it and then put it in water, and the water will not get in. That's because they are two separate environments. So you're gonna have a Docker container running on your computer. If you have Windows, you might have a Linux-based container running on your system. And so your friend who's running a Mac, they might also have that same exact Linux-based container on their computer. And if it was made from the same, essentially, thing, then you have the actual same computing environment. So now we've abstracted away from the need to really like overly understand or focus on the importance of the operating system-ish, because it's going to come back up in a second. And we've kind of, abstracted away from the need to overly understand certain things about our hardware, even though we do need to know a little bit. But we have enabled ourselves to now be able to share environments with other people, and actually on Acre. So that's another computing environment. It is amazing because you will all share the same, essentially, image. That's the template from which your containers are born. And so everyone has the same exact image, which is absolutely fantastic. And so we all are working in the same containers. When we send code to one another, we don't see like weird, version issues, conflicts, got to rebuild this, that, and the other. No, we're all in the same environment. So this Docker container. Again, we have whatever hardware-ish that we're running on here. We have our own operating system that's kind of between this virtualization or abstraction of Docker and its own container, separated from the behavior of our own host system. And that thing, the Docker engine, essentially is running all of our containers. All right, that was a mouthful. Any questions about that? Yes. I am so grateful that you asked that, because I meant to talk about that and then I didn't. So she asked, in what situations would you choose to use a virtual environment over containers? And so usually, if you are doing like something very quick, where you're trying to kind of understand like the MVP, so something that you're trying to put together like rather quickly to try to get a demo of or something like that, you might use a virtual environment because they're really easy to spin up. They're actually already installed like in your terminal, like it's really easy to use. Also, if you are, I think that's the main reason that one might use a virtual environment over a container. Also, containers can be just a little bit like heavy. So they do take like a little bit of a second to start. If you're like super impatient and don't have time for that, maybe you can do a lot of your work in a virtual environment, making sure to keep track of your package versions. And then you can kind of use that to initialize a container. But actually, I generally tend to work in containers. And again, I think that's really important for like academics from the reproducibility like point of view. And great question. Other questions? Oh, yes. Okay, perfect.
Could you take a package or a program that runs on Windows and run it on a Mac through a container?
So you would have to have the container that has the like behavior of the Windows machine. So you can run that on like a Mac, but it has to have like the right computational environment to reflect the Windows behavior. And so actually that gets to the heart of why there is a struggle with the M2s right now. So if I try to go and essentially use right now an M2 operating system in Docker, it is expecting to see like a Darwin or an OS X operating system along with the architecture, and that's, OS X is like proprietary. So that's the current struggle, but I'm sure someone will have a workaround soon enough. Okay, so now that we understand generally what Docker containers are, why we want to use them, why they are lovely, let's talk about how we can like make one. And it turns out it's not that bad, depending on your approach. And ChatGPT, great at writing Docker files, great. And so it has written a good number of mine, and it has done a great job. So what do we need to do to create these Docker containers? So number one, you will need to download Docker. It's the Docker engine. You saw that in the picture. It's got to run the Docker containers. You will need that. And also, it provides a really nice user interface if you don't want to use the command line. Command line can be a little scary. Beyond that, we get to the requirements. So requirements, they're just like a list of packages. They're like a list of packages in a file. So if you want to use Python, or not Python, but pandas, matplotlib, plotly, whatever Python packages are floating your boat, you can put them in the requirements file and then load that in with your Docker file. So this also says or don't. So put them in the requirements file or not. It works better in the requirements file because of the way that Docker builds and it helps with maintainability, but you can also literally put the list of the packages that you want in the container. So from there, we need to actually create the Docker file. So again, it's not that bad once you look at a few of them, but also again, ChatGPT is so GPT-4 is amazing for this. But let me show you what maybe they look like. And hopefully I can make these a little bigger than that. Oh, we're going to make it. Okay, great. Oh, sorry, people. Okay, so here's the Docker file. Remember that we said it's like giving somebody a little mini piece of an operating system with everything that it needs to run that particular application. That's what it's like. So we use our Docker file to build an image and use that image to build a container. So this essentially is the template, the written template of what needs to occur to make our environment for that computation be what we want it to be. So we're not going to go over every line of this because that would just be ridiculous, but we're going to go over the highlights of essentially what you're going to be doing. So at the very top, we can see the operating system and the version. So we just talked about that. You're giving somebody a little piece of an operating system, and so that helps to standardize the work between people. You at least have the same operating system. Then these, I don't know if you've ever had to install things like this, but it's essentially just packages that belong to the operating system. So sometimes you try to run maybe a new audio or theater or something that has to do with audio and video, and it'll be well, you don't have FFmpeg, and you say to yourself I don't know how to fix that. But this is how you would fix that. This is just how you get the relevant, oh, there it goes right there. In fact, we ran into that the other day, and that's why it's there. So you put it in this list, and it updates essentially this system with the relevant files that you need for your application to successfully run. Okay, again, we have all of the Python packages. They are arranged in a little bit of a weird way. That weird way is because of the caching system of Docker. Essentially, it's going to try to make it so that you don't have to write or you don't have to run it for a super long time. But essentially, you see all my Python packages. We have the development environment. You can see that we install using the requirements file. You can see that we install this thing from another package, but we install it from essentially source. We have another thing that we run, which is one of my favorite packages in the world. We can run startup scripts, so essentially whenever the Docker container starts, you can force it to do something. And we can also expose ports. Now what does that mean? So we literally just said that our Docker container completely separate from our operating system. It kind of sits on Docker engine. And so if you were to put our Ziploc container into water, there would be no leakage. But kind of that doesn't really help us, right? So it kind of does. But in a sense, you can imagine training a model. So let's say you train a model in this shelled off container. You do a great job. Model is perfect. Chef's kiss. And then once you close the container, because it is completely separate from your file system, your perfect model gone. We want to prevent such a thing. And so what we can do, so this doesn't go on, but anyways, so what we can do is we can create little holes where we pass things back and forth with the host operating system. And we can also create other little holes where we are able to access different ports. So if you use some development environments, they run servers so you can write code. These are essentially the standard servers. Oh, and I'm going extra long. Let me keep it moving. All right, and so this is the final command that we actually run. So whenever I start a container, it just pops that up. So then, this is the Docker file. What do we say we needed to do? Wonderful, Docker file, got it, exciting. Then we need to build the image from the Docker file. Now what does that mean? Again, it's meaning that the image is the template for the container. And so essentially, you can give people this image, and the image will define the behavior of the environment, so the container in which the computation will occur. Why did I just go backwards? Oh, because. So this is Docker Desktop. and it even says containers. So here, you can see the image that I built. There's 2 images here. One is this one. It has a particular kind of architecture. So this is for an ARM64 like interface, and then this one is for a more standard interface. And so here you can see 2 images. I can build containers from these, and I think Umang will show you a little bit more about this whenever you're going through the work for the DGXs. But essentially, you like run. So this is too little to read, but it does say Docker run. It's going to make it interactive. It's going to make it so it cleans up after itself. Here, you see this -v. This is where the volume is mounted. Again, we're passing things back and forth. This is the through way through which we're passing things. So here is my file path that I want to hook up to the Docker containers file path. So now anytime I save anything in this directory, it will be saved to my file system, even after the container closes. Here, we can also open up and connect some ports. So I want my port to be connected to the Docker containers port. Whatever it sees on that port, I want to see it too. So we can tie those together. And then this is the name of the image. So after we start that, let's see if we actually, can. But after we start that, you'll see that we get our application running. I can start that, I guess, but we'll come back to that. So right now, you've already seen that I've built the Docker file into an image, and now I'm running my application in the container. So what I can do is now I can start building my models, and I can give my friends and my teammates my image, and we can all have the same environment and stop fighting over package versions. Okay, so I think that actually was the end. Okay, I think that was the end, but I'm just going to show you, if I can, what the application is looking like. Oh, this is the port that I opened to the container that's running. You can see it here. So the application sort of that I wanted to have it running was Jupyter Lab. It just started that one. But now it's going to allow me to do all the training that I so well please. So here, this is the folder that's connected back and forth. You will see, if there's time, that essentially this llama recipes, it comes from the same Docker, the same procedure that Umang took to create a llama implementation or training on the DGXs. This AI training day, that should sound like the repo because it is. I cloned it like normal. Oh my gosh, that looks like all the same things that you were just looking at. Looking at this one, oh my gosh, that looks like the same exact notebook that you were looking at, except for I added a few things. So here you can see the platform on which this code is running. It says that it's running on Linux. That is the kind of container that it's in. I'm on a Mac, right? My host system is a Mac. This thing thinks it's running on Linux because I built it to think that it's running on Linux. So here you see a lot of the same things that you saw before. Again, the challenge right now with the Macs being able to actually train models has to do with some of the packages that are currently being built, and we can't fault them for that. I mean, it's open source, at least they're doing something. But there's still a few errors in there where we can't actually do this quantization very well. It doesn't like the way that we talk between the hardware of Apple and the Docker engine. It doesn't like that. And so they just need to do a little bit more work on that, and then I think that we will be ready to start training models thereafter. So again, exciting because whenever you are training models essentially in one place, the environment can look almost like the same for another place. So here again, this is the same repo. I could run it from top to bottom. If just bits and bytes was working, I already took the same steps as Umang did for training Llama, because the Docker containers is very similar. And so it's just very helpful to have this kind of software that will allow us to have the same containers as our teammates, but also have reproducible science. All right, so now I've talked about him enough, and it's his time to come up here. Umang, would you like to talk about the DGXs? All right.
Perfect. All right, can you hear me? Perfect, yes, I can hear myself. All right, so now I'm going to talk a little bit about how we can do this fine-tuning on the DGX A100s. It's kind of building on what Dr. Bell just talked about. But here, I'm logged into our DGX A100 in a terminal prompt. So I can just, see things about it. So I can see here that, this is the OS version that I'm running. It's DGX server. My architecture is x86. And I can see, all sorts of information about it. If I type NVIDIA SMI, I can also see information about the GPUs that I have. So I can see here that I have 8 GPUs. They have 80 gigabyte memory each, so it's a pretty powerful machine. But nothing is running on it right now, so let's change that. So you obviously won't be able to follow along unless you have access to the DGX. I think there might be one person apart from me here who does. But you log onto the DGX like you would any other sort of Linux-based server. And then the first thing that you want to do, again, is prepare the environment. So what I'm going to do is I'm going to navigate to a directory where I want to put everything. So I'm just going to do that. Maybe I'll make this a little bit bigger. All right, so I'm in here now. I can see that I have a couple of folders. I've done a little bit of prep work, so I don't need to run through all of this. But the main things that we need to do is create a directory, which I'm going to call Gemma FT for Gemma Fine Tuning. And the first thing that I'm going to do is clone a repository that's provided by Hugging Face. So TRL is a repository provided by Hugging Face, Transformer Reinforcement Learning. This is exactly what Miranda used to do the fine-tuning of Gemma that you just did in Colab. It's the exact same package, but we're going to use it a little bit differently. We're going to use it to do the fine-tuning through a command prompt. So the first thing we're going to want to do is just clone it. So what that looks like is just git clone, and you provide it the link of the repository, just like you would for anything else. Let me just go there. All right, and so I can see that I've already done that in here. So I can see that there's a folder called TRL here. If I were to further navigate into TRL, I will see that, okay, there's a lot of different things here. There's an inferencing Python file. There's setup configurations. The whole TRL package actually lives under here. There's Docker files. So basically, this entire repository is designed out of the box to be able to run like this. They've done a lot of the work for you, so you're not going to have to do too much. The first thing you're going to want to do once you've cloned this repository is create a Docker volume. Following the same steps as before, you would essentially use this command right here, and I'll paste it here. Not that. Let's copy that. So what this is basically saying, it's saying Docker volume create. So create a Docker volume that is linked to this specific folder, and it's linked to this specific Docker image. So here I have an image called, the specific Docker folder. So if I were to do this, it would create a new Docker volume where I can do all of my work. I've already done that because I'm in it right now, so I'll skip that step. But the next thing that you'd want to do is actually run the Docker container. So that would essentially, you'd use the same command that Dr. Bell just showed us. It will be Docker run. I'm going to tell it GPUs all because I want to use all 8 GPUs that are available to me. And then I'm going to say I want it to be interactive. I want it linked to this specific volume, which is Gemma FT, and then all the stuff that tells it that, okay, link it to Gemma FT so that it's storing information within the Docker container. And then I'm passing it the name of the Docker image that I want it to use. Currently, it's saying nvcr.io NVIDIA PyTorch. This is a pre-built container that NVIDIA provides that you can easily download. I'm not going to use that right now because I've already created a separate Docker image, and it's called Gemma FT. But essentially, that pre-built Docker container does all the work for you. You don't need to make the Docker file. You don't need to do any of that configuration. Pre-built, it can run pretty much all the things that we'll be running here, except for a few things. There are a couple of packages that specific Docker container does not come with. So here I ran the Docker container. It's saying, okay, it's a PyTorch container primarily. This is the PyTorch version, and a little bit more information from NVIDIA about how the container was built. I'm going to ignore all of that. The first thing you're going to want to do is update this Docker container to contain all the required packages that you'll need. So that includes upgrading pip so I can install the latest versions of everything. I'm going to install the Hugging Face command line interface. This will allow me to log into Hugging Face and provide that token that we've been using this entire day. And I'm also going to install and upgrade, that's the -u, all the packages that I need. So that's going to be the transformers package provided by Hugging Face, TRL provided by Hugging Face, PEFT provided by Hugging Face, and you guessed it, bits and bytes provided by Hugging Face. So just going to run that. It's going to install everything. It'll take a second. And while it's installing, let's take a look at our next step. So it says navigate to the TRL directory. We've already done that. But the next command is actually doing the training. We really don't need to do much. So accelerate is the package that we're going to use to do the main training that allows us to do distributed fine-tuning of the model. It basically spreads the entire model across 8 GPUs and the data so it can kind of do parallelized computing instead of just serialized computing on a CPU. I'm giving it config files. I'm giving it a specific YAML file, which is again a configuration file that'll tell it how to set up the entire training process. Again, this is stuff that I didn't make. This comes pre-built from Hugging Face. We made it super simple. Num processes up here, I've said 8. Num processes, basically how many GPUs do you have? I have 8. I could easily serialize this by saying 1, or I could use fewer. You just pass in a number depending on the number of GPUs you have. And then finally, the script that it's running, which is under examples, scripts, sft.py. And we'll take a look at that in a second. Nope, not there. So let's take a look at where we are right now. Now this is the Docker environment that we're looking at. We're inside the Docker container. We can see there's a couple of examples from NVIDIA. We're going to ignore that, but we really want to be in here, Gemma FT. So I'm going to do that. I'm going to go to Gemma FT. I'm going to see what's in here. So I still have that folder that I had created. So I'm going to go to TRL training. I can see there's TRL in here. So that's that step. So we are now where we want it to be. We navigated to Gemma/TRL. If we take a look here, it's the exact same thing that we'll see before. The examples, the scripts. If I go to examples, and I go to, where'd it go? Scripts. And I can see sft.py. That's the file that we're going to be running. And that's pre-built again. We don't really need to worry about it. I'm going to go up a few levels. And so let's take a look at that sft.py file and see that it is actually almost identical to the code that Miranda shared with us. So what it essentially is a modularized version of the code that we were looking at earlier. Basically what that means is instead of having to inside the code, so this is the trainer, SFT trainer that we saw earlier. Let me make this slightly bigger. This is the SFT trainer that we saw earlier. Instead of passing in here, say, Gemma 7b, I'm just passing in the model configuration. It's all stuff that's been modularized. I'm going to pass in all of these arguments through the command line using the command that I'm just going to run. Again, our training arguments are passed in through there. The training data set is passed in through there. All of it's just been modularized, so I don't really need to do a lot of thinking. So let's just do it. Here we are. So here's what we're going to do. We're going to simply just paste this in. So we're doing accelerate launch. We're providing a config files. We're saying number of processes is 8. We're saying you want to run the sft.py file. The model that I want to fine tune is Google Gemma 7b. Great. This is going to come directly from Hugging Face. The data set that I'm training it on is another data set that we haven't seen before, but it's Open Assistant. Open Assistant provides that. It's basically a data set that makes these models act like better chat models. I'm passing in all the training arguments, per device trained, batch size, the gradient accumulation steps, the learning rate, all the stuff that we saw earlier but kind of ignored. I'm also saying that I'm going to want to use PEFT, so this is saying that I want to use LoRa for the parameter efficient fine tuning. I'm passing in the LoRa parameters, so that's the ones that we also saw earlier, the target modules, and I'm also saying that I want to load it in 4-bit. So I'm using the quantized version, so it's going to just be a little bit faster. That being said, I don't need to do PEFD or load it in 4-bit because I have so much memory. I could just do a full supervised fine-tuning on this machine. But then again, we don't want to sit here for several hours. So we're going to just see what happens. But before I do that, before I almost forget, you still need to log into Hugging Face. So we're going to do that by just saying Hugging Face CLI. So that's command line interface, login. Okay, now it's just asking me for my token. This is the same thing that we saw earlier. I'm going to copy my read-write token, paste it in, and don't want to save it for now, and it says it's been successful. So now I can go back and run this script, and let's see what it does. It'll take a second to start, but we'll see very, very similar things to what we actually saw earlier, if it decides to work. Takes a second. So basically, it's setting up the environment, it's grabbing all the configuration files, it's setting up the multi-GPU processing, and there we go. So now it downloaded the tokenizer, it downloads it's downloading the map, it's downloading the data, it's downloading all the things that we need. And so here, now it's actually downloading the Gemma model. It'll take a second, but pretty much you'll see that it's going to do exactly the same things that you saw in the Python notebook. I'm not going to do this right now because it still takes about 20 minutes, but yeah, it'll be pretty quick. If you were to run this exact code on a single GPU, an A10 with maybe like 30 gigabytes of RAM, it will take about 9 hours. So it's very, very powerful. I'm just going to interrupt that for a second. So let's say that we've already fine-tuned it, which I have. So if we look here, there's a Gemma fine-tuned Open Assistant folder here. If I go in here and see what I have, you'll see that there's adapter configurations, adapter safe tensor. So this is actually the stuff this is the trained model. But it's not exactly the trained model. So remember when Jesse said when we're doing LoRa, we're actually not training the entire model, we're just training select parameters. So what this has done is it's only saved those select parameters. So what this is like a partial model. Now what we're going to want to do is take this partial model, merge it with the original model that we had so that it's now the full parameter efficient fine-tuned model, and then we can inference on it. So I created an inferencing script. So it's right here in the markdown file that we're looking at. So I touch inference.py basically means create a file called inference.py. Vim allows me to edit it within a command prompt. But essentially what we're doing is we're importing all the libraries, PEFD, transformers, everything. I'm grabbing the base model, which was Google's 7 billion parameters. This could be any other model as well. And then the adapter model name. So this is where I'm just passing in the name of the folder where the model parameters were saved after training. And then I load the base model, and then using the PEFD model sub kind of module from transformers package, I merge them. So I'm combining the PEFD adapters and the base model. And then I also obviously grab the tokenizer. It needs to be the exact same tokenizer for the model that you're using. Device, I'm just going to do inferencing on the CPU right now, just because. And then I'm just providing in an input. This movie was really fill in the blanks and just model.generate, and it'll print an output. So let's try and run that. So you just do Python, and then let's go up a directory. We can see that there's the inference.py file, and to run a Python file within this Docker container, super easy. Just say Python inference.py, and you run that. And so it's going to download the model again. It's going to combine the model with the adapters, and then it's going to do the actual inference on it. This takes a second because we're doing it on the CPU, but again, yeah, it's going to download the entire model. But it's that simple. They've made this very, very straightforward. And the best thing about this is that this isn't specific to Gemma. This is specific to literally any model that is available on Hugging Face. So if you needed to do some fine-tuning and you had access to one of our DGXs, or really any other NVIDIA-based machine, you could follow these exact steps, use that really one line of code with a lot of parameters here, and just do your fine-tuning on literally any model that Hugging Face offers without having to, write your training loops and write any code. You just clone a repository and tell it the model that you want to fine tune and give it some parameters, and there you go. You have now successfully fine-tuned a large language model across 8 GPUs very, very easily. I need to point out that this is so easy. This was not possible earlier. You know, in order to do distributed model training, you had to do tons of setup, including creating the Docker file. But that was like the easier stuff. But you'd need to do a lot of stuff with PyTorch to ensure that your environment is set up correctly. But now all you need to do is run one line of code, and you can pretty much do anything, depending on, you know, the main work still is prep your data set, ensure your data set looks the right way for the model that you're working on, ensure that your, you know, parameters that you're passing in are appropriate for the model, you know, your learning rate, your gradient accumulation steps, all that stuff. And those things are also provided by the model builders, so you really also don't need to kind of think about what those parameters should be. You can just use it out of the box and just make a few minor edits to this code, and then there you go. You've fine-tuned a model really, really quickly, very, very easily. Questions about this whole process? Yeah.
Have you got any examples at the Data Institute for, I'm sorry, I didn't see you there. Do you have any examples at the Data Science Institute for training image models?
We have done that, so I'm sure you could reach out to one of us, and then whoever worked on the project who was working with images can guide you accordingly. But yeah, we've worked with image models. We've worked with pretty much everything except video models, because that's just really, really new. But yeah.
Thank you.
Other questions?
This may be a really dumb question, but when you talk about like the model, what kind of file is this, or what kind, like how many files is a model, or how is it an XML, a spreadsheet? What is it?
It's a combination of a lot of different files. I think the .pt file that you're saving at the end of the Colab notebook that Miranda showed you is sort of the main chunk of the model. That is like a fully fine-tuned model, but it's a combination of a lot of different files. Yeah, that's kind of what I would say.
So on a related question to that, is the model something then that we could download that object and upload it into like a protected environment if we are using secure data?
Yeah, you could totally do that. So once you fine-tune this, you'd basically copy this Gemma fine-tuned Open Assistant folder. This is all the PEFD configuration. Then you'd also download the Gemma model from Hugging Face, combine them in your local environment, wherever that is, and then use it. Yeah. Other questions? Cool. All right, I think I'm going to hand it off to Jesse, and thank you so much. Yeah. Oh, yeah, and it maybe 3-4 minutes, but you'll see at the bottom here, this is the output. The input was, the movie was really good, and then I asked it to complete the sentence. This movie was really blank. This movie was really good. It was a little slow at the beginning, but it picked up. So you can inference on it like that, or you could, you know, just put a front end on this, like a Gradio or a Streamlit application, and have the model running in the back, and then you'd have a, you know, UI that you can interact with this model.
So a few additional comments about what we just did. So training a model and adding new capabilities, doing domain adaptation, coming up with a new version of the model is something that was the province only of very large tech companies up until just a few months ago. So with parameter-efficient fine-tuning, we're able to create new types of models. Remember the tree that I showed you at the very beginning? And remember that the difference as you moved up the tree was the data that you trained on. So now what we have is the capability of creating brand new kinds of models with new capabilities, and we can do that with compute that we have here at Vanderbilt. So I charge you to think about your areas of study, to think about what model capabilities would allow you to move your work forward or to solve problems that you couldn't really approach before. And then come and talk to us. Maybe you'll be able to train this just on your own Mac. Maybe you'll be able to train this on Google Colab. But if you need the additional compute, that's why Vanderbilt's made an investment in these DGX A100 systems that we have, specifically so we can address these kinds of problems. And now, these parameter-efficient fine-tuning methods are coming up to meet us and to give us capabilities that we were not really anticipating having, but now we have in hand. So I'll point out a couple of additional things here, and then we'll be wrapping up. One, you'll notice up here where it says LoRa. So LoRa, let's see, does it still have LoRa up here? Heft, yeah, parameter-efficient fine-tuning, and the specific type of parameter-efficient fine-tuning that we were using was called LoRa. Well, just 2 weeks ago, a new approach based on LoRa called DORA was released, which is even more performant and has even more capabilities and can do so with less compute. So already, even now, we're beginning to see improvement in what is possible. The brand new method that we can't even show you here because there aren't common techniques, the training by proxy is another example of techniques that make it possible to create models that have top level capabilities that we can train again. But the difference is, and what we need to train the models is data. So that's the recurring theme here. What's the difference between all the models? It's not architecture. The morning that we spent going through the architecture, that's the same for Llama, it's the same for Gemma. All of these look almost identical with different choices for some parts of the models, but it's the data. So again, I charge you. Think about your data. Think about what a general purpose learning algorithm could do with your data. And remember, it doesn't have to be text. It can be video, it can be audio, it can be multiple modalities. So I invite you to come and join us at the Data Science Institute on Fridays, 10 to 12, open door. We have really good coffee. We'd love to have you come by and for us to talk about possibilities of training custom AI models. Well, let me close up here. And actually what I'll do is I'll ask the folks up above to go ahead and put the slide deck up that we have during the interstitial periods. You'll find information up here on the slide deck with various programs that we have. We'll be doing an update on all the information that you've just heard here in May in what we call our AI Summer. It's 4 weeks. We do it Monday, Wednesday, Friday. Is that what we agreed on? Did we agree Monday, Wednesday, Friday? I think we did. So Monday, Wednesday, Friday throughout all the months of May. It is free for Vanderbilt community, for community members, for VUMC. We'll have availability also for industry partners as well. This will be an opportunity to dive even more deeply into this technology. Plus, you'll have the update of what's happened between now and May, which will be a lot. So we'll be covering the new technology at that time. So let me close this out here. I'd like to thank you all for spending the day with us and for learning about AI. Congratulations on some of you who trained the first model ever, and congratulations to everyone for making it through a lot of information throughout the day. I'll take final questions that anyone has, questions about this material, questions about the compute, or questions about AI in general. Very good. The team and I will be hanging out here to take questions that you might have. Happy to answer or happy to talk more in depth about ideas that you might have for projects in the future. Have a great day.